Please subscribe to support the channel. We're standing on a tiny rock orbiting an average star, yet above us lies one of the greatest mysteries of the universe, a cosmic monster hiding in plain sight at the heart of our own galaxy. It's invisible to the naked eye, but its gravity rules over billions of stars, including our sun. Astronomers call it Sagittarius A, the supermassive black hole that anchors the Milky Way. If our galaxy were a city, Sagittarius A would be the central power station, silent most of the time, but capable of reshaping everything around it. The idea that there's a colossal black hole just 26,000 light-years from us may sound like science fiction, but it's not. It's science fact, and it's one of the most important discoveries in modern astronomy. Over the next few hours, we're going to peel back the layers of mystery surrounding Sagittarius A, exploring not just what it is, but how we discovered it, how it shapes our galaxy, and why studying it is one of the greatest triumphs of human curiosity and technology. Now, let's talk about what Sagittarius A actually is. At its core, Sagittarius A is a supermassive black hole. That term, supermassive, isn't exaggeration. This object weighs in at about 4 million times the mass of our Sun. Imagine combining 4 million suns into one single entity. But instead of spreading out across a vast space, all that mass is squeezed into a region smaller than our solar system. That's what makes it a black hole. Its gravity is so overwhelming that nothing, not even light, can escape its pull once it gets too close. Unlike stars or planets, you can't see Sagittarius A directly. It doesn't shine with its own light. Instead, it reveals itself through its influence, the way it bends spacetime, the way it accelerates stars, and the faint glow of gas and dust as they spiral toward their doom. In many ways, Sagittarius A is both a monster and a mystery, an invisible giant that silently dictates the dance of the Milky Way. Next, let's ground ourselves in space and talk about its location. Sagittarius A sits at the very center of our Milky Way galaxy, about 26,000 light-years from Earth. To put that distance into perspective, 1 light-year is nearly 6 trillion miles. So even though Sagittarius A is in our galactic neighborhood, it's unimaginably far by human standards. Its coordinates place it in the direction of the constellation Sagittarius, which is why it bears the name. When we look toward that constellation on a clear, dark night, we're actually staring toward the densest region of our galaxy, filled with stars, gas clouds, and dust lanes. Behind that veil lies the supermassive black hole, hidden from direct view but unmistakably present. What makes its location fascinating is that it's not just the center of the Milky Way in terms of position, it's also the gravitational anchor that holds our galaxy together. Without Sagittarius A's immense pull, the spiral arms of the Milky Way might not be as stable as they are today. So when we talk about our galaxy's center, we're really talking about Sagittarius A's throne in the cosmic theater. Now, let's trace the story of how we discovered this hidden giant. For decades, astronomers suspected something unusual was lurking at the heart of the Milky Way. In the mid-20th century, radio astronomers picked up an intense source of radio waves coming from the constellation Sagittarius. At first, it was just a curiosity, a strange, compact signal buried in the galactic core. But as telescope technology improved, astronomers noticed something even stranger. The stars near the galactic center weren't moving in smooth, predictable patterns. Instead, they seemed to be whipping around at incredible speeds, as if being pulled by an invisible force. It was like watching leaves swirling in a whirlpool with nothing obvious at the center. This was the first big clue. Over time, precise measurements of stellar motions revealed that these stars weren't just orbiting something massive, they were orbiting something compact, something that couldn't be a cluster of stars or gas. The only explanation that fit was a black hole, and not just any black hole, but a supermassive one. The suspicion became stronger in the 1990s, when long-term monitoring began to track the stars in exquisite detail, proving once and for all that something extraordinary was hiding in the darkness. Now, let's dive deeper into how astronomers measured its mass, because this is one of the most elegant achievements in astrophysics. The key lies in a star called S2. S2 is one of the many stars near the galactic center, but it became a superstar in astronomy because of its orbit. This star completes a full orbit around Sagittarius A every 16 years. That might not sound fast compared to planets in our solar system, but think about the distance. It's circling an invisible object 4 million times the mass of our Sun in just over a decade and a half. At its closest approach, S2 whips around at speeds of more than 7,000 kilometers per second. That's about 2.5% the speed of light. By carefully tracking its movement with telescopes like the Very Large Telescope in Chile and the Keck Observatory in Hawaii, astronomers were able to calculate the exact mass of the object it orbits. The math is simple but profound. Only a supermassive black hole could explain S2's orbit. No cluster of stars, no dark matter cloud, nothing else would fit. This star essentially gave us the weighing scale for the monster at the heart of the Milky Way. It was the smoking gun that proved beyond doubt that Sagittarius A is real, and it's every bit as massive as theory predicted. Sagittarius A is not just another object in the sky, it's the very definition of extreme. When we say it's a black hole, what we really mean is that it's a region of space where gravity has gone beyond all reasonable limits. Unlike stars or planets that have a surface, Sagittarius A has no solid boundary. Instead, it has an event horizon, an invisible one-way door that marks the point where escape is impossible. Once anything, whether light, gas, or even entire stars, crosses that threshold, it can never return. That alone makes it alien compared to anything we experience in daily life, but the scale of Sagittarius A pushes it into the realm of the extraordinary. This isn't a small black hole created by the collapse of a single star. Those are called stellar mass black holes, and they usually weigh anywhere from a few to maybe 100 times the mass of the Sun. Sagittarius A is in a completely different category, a supermassive black hole. Its mass is about 4 million times greater than the Sun's. To grasp how staggering that is, consider this: our Sun already contains 99.8% of the total mass of the solar system. Every planet, moon, asteroid, and comet combined make up just a tiny fraction of what the Sun holds. Now multiply that Sun by 4 million, and you have the gravitational titan sitting at the Milky Way's core. But here's where the black hole nature really bends the mind. Despite being so incredibly massive, Sagittarius A is surprisingly compact. All of that unimaginable mass is compressed into a region about 25 million kilometers across. That's roughly the size of Mercury's orbit around the Sun. Think about that for a second. You could fit 4 million suns into a space no larger than the tiny inner part of our solar system. That's the power of gravitational collapse. It takes matter and crushes it down until physics as we know it breaks apart. Now, some might wonder why such a monster doesn't tear the Milky Way apart. The key lies in the way gravity works. Sagittarius A's influence is strongest near its center, but as you move farther away, the Sun's gravitational pull over Earth is far more dominant. That's why we orbit the Sun and not the galactic black hole. Still, the combined pull of Sagittarius A is what ultimately keeps the entire galaxy, its stars, its spiral arms, and its overall structure, bound together. It's like the anchor pin in an enormous carousel. Without it, the stars of the Milky Way might drift into intergalactic space. Another way to think about Sagittarius A is as a paradox. On one hand, it's invisible, completely dark, because not even light can escape. On the other hand, it's one of the brightest sources of energy in certain wavelengths, particularly radio waves, because of the way matter interacts with its gravity before disappearing. This duality makes it both a hidden monster and a shining beacon of astrophysical activity. It challenges us to rethink our understanding of visibility and presence. Something can dominate the structure of a galaxy without ever shining like a star. Sagittarius A also represents an evolutionary puzzle. How did something so massive form in the first place? The Sun took shape from a cloud of gas and dust collapsing under gravity. But you can't simply collapse a star into a 4 million solar mass black hole in one step. The leading theories suggest that Sagittarius A may have grown over billions of years by consuming stars, gas clouds, and even merging with other black holes. Each feast added to its mass, slowly transforming it into the supermassive entity we see today. Yet, the timeline doesn't always fit neatly, because astronomers have found black holes of similar or even larger mass in galaxies much younger than ours. That raises fundamental questions. Did Sagittarius A form from the direct collapse of an enormous primordial gas cloud in the early universe? Did it grow rapidly through runaway mergers? These mysteries are part of why Sagittarius A is such a compelling subject for ongoing research. The comparison with our Sun is also fascinating on a more personal scale. The Sun is the lifeblood of Earth. Its energy fuels photosynthesis, drives our weather, and makes life possible. Sagittarius A, by contrast, is utterly indifferent. It doesn't shine with life-giving light. It doesn't warm planets. Instead, it bends spacetime itself, governs stellar orbits, and swallows anything that strays too close. If the Sun is the nurturing parent of our solar system, Sagittarius A is more like the ancient, silent ruler of the galactic empire, rarely seen, but always in control. Its sheer mass also makes it a natural laboratory for testing the most profound laws of physics. Einstein's theory of general relativity predicts how space and time are warped by gravity, and Sagittarius A provides one of the best testing grounds in the entire universe. The way stars orbit it, the way light bends around it, and the way time itself slows in its vicinity, all of these phenomena allow scientists to push the limits of physics in ways no earthbound experiment ever could. That's one of the reasons why astronomers have dedicated decades to observing it so meticulously. In many ways, Sagittarius A represents the culmination of cosmic extremes. It's heavy beyond imagination, yet it takes up a surprisingly small volume of space. It's invisible, yet it reveals itself by dominating everything around it. It's ancient, yet it continues to evolve as it interacts with its environment. To call it simply a black hole almost feels insufficient. It's a cornerstone of the Milky Way, a keystone in the puzzle of galactic evolution, and one of the most profound reminders that the universe is stranger than we can ever fully grasp. And yet, despite its incomprehensible nature, Sagittarius A is intimately tied to us. Every orbit the Sun completes around the galactic center, once every 225 million years, is dictated by this giant's presence. Our entire existence, from the rise of the dinosaurs to the present day, has unfolded under its quiet watch. In that sense, Sagittarius A is not just a distant curiosity, it's part of our cosmic story, shaping the very galaxy we call home. When we talk about Sagittarius A's location, we're essentially pointing to the very heart of the Milky Way galaxy. Our galaxy, a vast spiral system of hundreds of billions of stars, stretches more than 100,000 light-years across. It's easy to think of it as an abstract swirl seen in textbook images, but it's real, and Sagittarius A sits right at its gravitational center. If the Milky Way were a spinning disk, Sagittarius A would be the pin in the middle, quietly keeping the entire structure bound together. Now, the distance is key to understanding where it lies in relation to us. Sagittarius A is about 26,000 light-years away from Earth. That means if a photon of light were emitted near the black hole at the exact moment the first human ancestors started walking upright on Earth, that same photon would only now be reaching our telescopes. To put that in earthly terms, 1 light-year is roughly 6 trillion miles. Multiply that by 26,000, and you begin to grasp the scale of separation between us and this cosmic monster. Even traveling at the fastest speed humanity has ever achieved with a spacecraft, it would take tens of millions of years to reach it. So where do we look to find it? Its position lines up with the constellation Sagittarius, the Archer. From our vantage point on Earth, when we gaze into Sagittarius on a dark, clear night, we are staring into one of the densest and most spectacular regions of the sky. This is the direction of the galactic bulge, the crowded hub of stars, gas clouds, and dust lanes that form the Milky Way's nucleus. The sheer density of stars here is staggering. While in our part of the galaxy the nearest star is over 4 light-years away, in the galactic center region, stars can be separated by just light weeks or even light days. It's an environment buzzing with activity, and Sagittarius sits hidden in the very core of it all. But locating Sagittarius A isn't as simple as just pointing a telescope at Sagittarius. The line of sight from Earth to the galactic center passes through enormous clouds of interstellar dust and gas. These clouds obscure visible light, making the core of the Milky Way appear as dark streaks across the sky to our eyes. That's why we can't just see Sagittarius A with an optical telescope. Instead, astronomers turn to wavelengths that can pierce through the dust, like infrared and radio waves. These tools allow us to peer past the cosmic veil and zero in on the compact, energetic radio source that reveals the black hole's location. The constellation connection also gives this black hole its name. In astronomical catalogues, when a strong radio source was first detected in this region, it was labeled Sagittarius A, with denoting it as the brightest source in Sagittarius. Later, the supermassive black hole itself was identified as the strongest part of that source, and that's how it came to be called Sagittarius A. In other words, Its name is less about poetic imagination and more about the practical cataloging of cosmic signals. But still, there's something fitting about placing such a powerful cosmic entity in Sagittarius, a constellation symbolized by the archer aiming toward the galaxy's heart. Its central position isn't just a curiosity, it has consequences for the entire Milky Way. The black hole's immense gravitational influence extends far beyond its immediate vicinity. Though its direct dominance only stretches across a few dozen light-years, its role as the anchor point ensures that the spiral arms and galactic disk rotate in a stable way. Without such a massive anchor, the galaxy's structure would not be as coherent. Every star you see in the night sky, including our Sun, orbits around this shared center, completing a circuit roughly once every 225 to 250 million years. Earth has orbited Sagittarius a fewer than 20 times in its entire 4.5 billion-year history. That means the dinosaurs lived during one of our previous galactic laps, and humanity's entire existence has unfolded in just a fraction of one orbit. Another fascinating aspect of its location is its role as a natural boundary in our observations. When astronomers map the galaxy, Sagittarius A provides a fixed reference point. Its unique radio signature makes it a galactic landmark. No matter where you are on Earth, no matter what telescope you use, that compact radio source sits at the heart of the Milky Way, guiding astronomers to the galactic center like a cosmic beacon hidden behind dust clouds. If you were to travel towards Sagittarius A, the sky would transform dramatically as you approached the galactic center. Stars would grow denser and denser until they looked like swarms of glowing fireflies packed across the heavens. Eventually, you'd find yourself in a stellar metropolis, where stars orbit at blistering speeds, supernovae erupt more frequently, and gas clouds collide in violent bursts of star formation. And in the very heart of that chaos sits Sagittarius A, invisible yet undeniably present, the anchor holding it all together. So while we can't see it with our eyes, knowing where Sagittarius A is gives us a sense of place in the galaxy. We live in one of the outer spiral arms, far removed from the dense, turbulent core. But every time we look towards Sagittarius on a summer night, we're facing the galactic capital city, and beyond those shining lanes of stars lies the throne of the Milky Way, the supermassive black hole at its center. The discovery of Sagittarius A wasn't a single eureka moment where someone pointed a telescope and immediately shouted, "There's a black hole." Instead, it was a decades-long detective story, with scientists slowly piecing together clues from strange and subtle evidence. And the earliest hints came not from seeing the black hole directly, because that's impossible, but from noticing that something invisible was exerting a powerful gravitational influence at the very center of the Milky Way. Let's roll back to the mid-20th century, when astronomers first began to seriously probe the galactic core using radio telescopes. In 1931, engineer and amateur astronomer Karl Jansky discovered that the Milky Way center was emitting strong radio signals. At first, the exact nature of this source wasn't understood. By the 1950s and 60s, radio astronomy had become a more advanced science, and astronomers identified a compact, bright source of radio waves in the direction of Sagittarius. They named it Sagittarius A. At that time, it was thought of as simply a curious radio object in a very busy part of the sky. No one yet realized that it was tied to a black hole. The breakthrough came in the following decades as telescopes improved, particularly in the infrared and radio bands. Astronomers began focusing their attention on the stars near the galactic center. To their surprise, these stars weren't drifting lazily around as one might expect in a dense cluster. Instead, they were moving at astonishing speeds, hundreds and even thousands of kilometers per second. It was as if they were caught in the gravitational grip of an invisible giant. Imagine standing at the edge of a merry-go-round and watching children whip around at impossible speeds, far faster than any visible rider could reasonably hold them. Something unseen was pulling the strings. One of the key puzzles was that the volume of space in which these stars were moving so erratically was incredibly small compared to the scale of a galaxy. If the mass causing their motion was spread out, say, among millions of stars, clusters, or even dense clouds of dark matter, those stars wouldn't have been able to orbit so tightly and so quickly. The only explanation that fit the data was a single, incredibly massive, and compact object. Already, astronomers were starting to whisper about the possibility of a black hole. Throughout the 1970s and 80s, scientists began using more precise measurements to track the movements of these central stars. Technology like speckle imaging, which corrected for the blurring effects of Earth's atmosphere, revealed just how fast these stars were flying around. Their motions weren't random, they were orbiting something. And whatever that something was, it had to be millions of times the mass of the Sun. Yet, there was nothing visible there in optical wavelengths. No cluster of stars, no bright source of light. Just emptiness, except for that mysterious radio beacon, Sagittarius A. The idea that the Milky Way center might harbor a black hole began to gain traction. Theorists pointed out that if black holes could form from dying stars, then perhaps galaxies could grow giant versions in their hearts. This would also help explain why other galaxies, especially those with active, quasar-like cores, were so luminous. Their brilliance could come from matter falling into supermassive black holes. Sagittarius A seemed to be the local, quiet cousin of those galactic monsters. Still, the scientific community is cautious, and extraordinary claims require extraordinary evidence. It wasn't enough to say the stars were moving oddly. Astronomers needed to calculate orbits, track them for years, and show that they matched predictions for motion around a single compact mass. This set the stage for the groundbreaking observations that would follow in the 1990s and 2000s, when teams led by Reinhard Genzel and Andrea Ghez would track the orbits of individual stars in exquisite detail. Their data would ultimately prove, beyond reasonable doubt, that Sagittarius A was a supermassive black hole. But in those earlier decades, the discovery process was more about suspicion and accumulation of clues than outright confirmation. The unusual motions of stars near the galactic center were the first breadcrumbs leading scientists to the monster in the shadows. They knew something powerful was there, something far too compact to be anything but a black hole. It was as though the galaxy itself was hiding a secret right at its core, and only by watching how the stars danced around it could astronomers begin to guess what was hiding in the dark. This was an extraordinary shift in perspective. For centuries, the center of the Milky Way had been a mysterious and almost mythical concept. Now, astronomers were beginning to realize that the very core of our galaxy was home to a gravitational abyss millions of times more massive than the Sun. It was a radical idea, but the evidence was mounting, and the strange stellar dances were too compelling to ignore. When astronomers suspected that something enormous yet invisible was lurking at the Milky Way's core, they knew the only way to prove it was to weigh it. But how do you measure the mass of something you can't see, something that doesn't emit light? The answer lies in gravity's fingerprints. If you can observe how objects move under the pull of gravity, you can deduce the mass of the unseen force tugging on them. This is exactly how astronomers confirmed the mass of Sagittarius A, and the star that became the linchpin of this detective story was one known as S2. S2 is a hot, young star orbiting incredibly close to Sagittarius A compared to other stars. What makes it so special is that its orbit is not measured in thousands of years like most stars far out in the galaxy. It completes a full loop in only about 16 Earth years. That makes it possible to observe its entire journey around the black hole within a human lifetime. This is a rare and golden opportunity, because usually the cosmic timescales involved in stellar orbits are too long to study in detail. In the 1990s, two teams of astronomers, one led by Reinhard Genzel at the Max Planck Institute in Germany and the other by Andrea Ghez at UCLA, began painstakingly tracking S2 and other stars near the galactic center. They used some of the most powerful telescopes on Earth, the Keck Observatory in Hawaii and the Very Large Telescope in Chile. These observatories used adaptive optics and other techniques to correct for the blurring caused by Earth's atmosphere, allowing them to capture crisp, high-resolution images of stars orbiting in the crowded galactic core. What they saw was breathtaking. S2 was racing around an invisible point at blistering speeds. At its closest approach, called periapsis, it came within just 120 astronomical units of Sagittarius A. That's only about 3 times the distance between Pluto and the Sun. For a star to orbit so close, it must be tethered by an immense gravitational force. And the speed? At its fastest, S2 hurtled through space at over 7,600 kilometers per second, more than 2.5% the speed of light. Nothing less than a supermassive black hole could hold it in such a tight, furious orbit without tearing the star away. By applying the laws of orbital mechanics, laws first developed by Johannes Kepler and later refined by Isaac Newton and Albert Einstein, astronomers were able to calculate the mass of the object S2 was orbiting. The math pointed to an astonishing figure, about 4 million times the mass of the Sun, all crammed into a space smaller than our solar system. This was the smoking gun. No star cluster could possibly be that dense without collapsing under its own gravity. No exotic alternative, such as a dense swarm of dark matter or neutron stars, could explain both the mass and the compactness. The only explanation left was a supermassive black hole. The orbit of S2 also allowed astronomers to test Einstein's theory of general relativity in an extreme environment. When S2 swung close to Sagittarius A in 2018, scientists observed the star's light being stretched by the intense gravity, a phenomenon known as gravitational redshift. Just as Einstein predicted, the star's spectrum shifted toward the red end of the scale because time itself was running more slowly near the black hole compared to farther away. This was a direct and profound confirmation of relativity, using a star orbiting a supermassive black hole as the experimental setup. What's truly remarkable is the patience and precision involved in these measurements. It took decades of careful monitoring to trace the full orbit of S2. Each year's observations added a new piece to the puzzle, and by the early 2000s, the evidence was overwhelming. Both Genzel's and Ghez teams had independently measured the same result. Sagittarius A weighs in at 4 million solar masses. Their work was so groundbreaking that in 2020, Reinhard Genzel and Andrea Ghez were awarded the Nobel Prize in Physics for their discovery. And S2 isn't alone. Other stars near the galactic center, sometimes called S-stars, have also been tracked, each orbit further tightening the constraints on the black hole's mass and location. But S2 remains the poster child because its orbit is both tight and fast enough to provide clear, definitive results. The star has become something of a celebrity in astrophysics, a lone performer dancing around an invisible partner, revealing through its graceful, frantic motion the true nature of its companion. To put this achievement in perspective, imagine trying to weigh an object you cannot see across a gulf of 26,000 light-years by tracking a single point of light moving through a sea of other points of light. It's like watching a firefly buzz around in the distance and deducing the weight of the rock it's circling, even though you can't see the rock itself. That's the level of ingenuity, persistence, and technological brilliance involved in the measurement of Sagittarius A's mass. This was the turning point where suspicion became certainty. For decades, astronomers had wondered if the Milky Way harbored a hidden giant. Thanks to the orbits of stars like S2, we now know beyond doubt. The heart of our galaxy is dominated by a supermassive black hole, weighing millions of suns, silently shaping the Milky Way's destiny. For decades, Sagittarius A was the ultimate unseen giant, its presence confirmed by stellar orbits, its mass measured with exquisite precision, yet its face still hidden from us. Astronomers knew it was there, and they could calculate its size and weight, but they couldn't actually see it. Then came one of the boldest scientific projects of our time, the Event Horizon Telescope, EHT. This international collaboration set out to do what once seemed impossible: capture the very first image of a black hole. The challenge was immense. A black hole, by definition, doesn't emit light. You can't see it directly. The only thing you can hope to capture is its shadow, a dark silhouette created when the black hole bends and traps light around it. This shadow is outlined by the glowing radiation from superheated gas swirling in the accretion disk. It's like trying to photograph the rim of a whirlpool by the spray of water around it. And in the case of Sagittarius A, the whirlpool sits 26,000 light-years away, buried behind dust clouds, surrounded by chaotic stars, and flickering unpredictably as matter falls into it. To take such a picture, astronomers needed a telescope the size of the Earth. Building one physically was, of course, impossible. Instead, they used a technique called Very Long Baseline Interferometry, VLBI, which links radio observatories across the planet into a single, synchronized virtual telescope. By combining signals from dishes in Chile, Spain, the United States, Mexico, Greenland, Hawaii, and even the South Pole, the EHT achieved the resolution necessary to spot something as small as a grapefruit sitting on the moon. The first triumph of the EHT came in 2019, when the team released the groundbreaking image of the supermassive black hole in galaxy M87. That iconic orange donut of light proved the technique worked. But imaging Sagittarius A was always going to be more difficult, despite being much closer to us. Why? Because Sagittarius A is much smaller than M87's black hole. M87's monster weighs 6.5 billion solar masses, while Sagittarius A is only 4 million. This means that gas whirls around Sagittarius are much faster, completing orbits in minutes instead of days. To an observer, its appearance flickers and changes constantly, like trying to photograph a candle flame in a storm. Capturing a stable image required years of painstaking data analysis and computer modeling. Finally, in May 2022, the Event Horizon Telescope collaboration unveiled the long-awaited image of Sagittarius A. What the world saw was a glowing, lopsided ring of light surrounding a dark central shadow, the unmistakable silhouette of a black hole. It looked remarkably similar to M87's image, confirming Einstein's theory once again. Despite being different in size and environment, black holes share the same fundamental structure. That image wasn't just a photograph, it was a scientific milestone. For the first time, humanity had laid eyes on the very heart of our own galaxy. The fuzziness of the ring was expected, a result of the rapid variability and the intervening gas and dust, but the key feature, the dark shadow about 50 microarcseconds across, was clear and undeniable. For perspective, that's like seeing a donut on the surface of the moon. The fact that we could capture such detail across 26,000 light-years is a testament to the precision of global cooperation, atomic clock synchronization, and petabytes of data processing. The achievement was about more than just an image. It gave astronomers direct confirmation of the size of the event horizon, which matched perfectly with predictions based on S2's orbit and other measurements. It allowed them to test theories of accretion and magnetic fields in extreme gravity. It opened the door to studying black holes not just as abstract math, but as real, observable objects. And perhaps most importantly, it became a symbol of human ingenuity. The image of Sagittarius A is the product of hundreds of scientists from across the world, working together, sharing data, and pooling resources. No single country, no single observatory, could have done it alone. It's a triumph of global science, proof that when humanity unites to answer profound questions, the impossible becomes achievable. For generations, the center of the Milky Way had been a place of myth and mystery. In 2022, it became a place of direct observation, with a face that we could finally glimpse. That glowing ring around the darkness isn't just the image of a black hole, it's a window into the most extreme physics of the universe, and a reminder that even in the vast, unreachable distances of space, human curiosity can shine a light into the shadows. At the most basic level, a black hole is gravity taken to the absolute extreme. Everything in the universe that has mass, stars, planets, even you and me, bends the fabric of space and time around it. This is what Einstein showed us in his theory of general relativity. Mass and energy warp spacetime, and that curvature is what we feel as gravity. For most objects, this bending is relatively gentle. The Earth bends spacetime just enough to keep the Moon circling it. The Sun bends it enough to keep the planets in orbit. But in the case of a black hole, mass has been compressed into such a small, dense region that the curvature becomes infinitely steep. It's like the fabric of space itself has been pinched into a funnel so deep that nothing can climb back out. The defining boundary of a black hole is called the event horizon. This is the ultimate point of no return. If you cross it, you're gone forever. Not even light, which moves faster than anything else in the universe, can escape once it passes this invisible boundary. That's why the term black hole is so apt. It's a region of space from which no information, no matter, no energy can ever come back. To the outside world, it appears as pure darkness. But how do such strange objects form? The small black holes we call stellar mass black holes are born when massive stars reach the end of their lives. When a star several times heavier than the Sun runs out of nuclear fuel, it can no longer resist the inward pull of gravity. The outer layers may explode outward in a supernova, but the core collapses under its own immense weight. If the collapsing core is heavy enough, nothing can stop it. The matter gets squeezed down into an incredibly dense point, and a black hole is born. Supermassive black holes, like Sagittarius A, are different beasts altogether. They're millions to billions of times heavier than the Sun, far beyond what a single star could produce. Scientists think they may form in the early universe from direct collapse of enormous gas clouds, or by smaller black holes merging and growing over billions of years. However they come to be, the end result is the same. An object so dense, so compact, that its gravity rules everything around it. One way to think about it is to imagine taking the Sun, which is already huge, and squeezing it into a sphere only about 6 kilometers across. That's the size of a black hole with the Sun's mass. Now imagine multiplying the Sun's mass by 4 million and squeezing that into a sphere about the size of Mercury's orbit. That's Sagittarius A. The more mass you pack in, the larger the event horizon, but the density is always extreme beyond comprehension. Inside a black hole, our current physics begins to fail us. At the very center lies what we call a singularity, a point where matter is thought to be crushed into infinite density, and where the known laws of space and time break down. In reality, physicists believe there must be a deeper theory, perhaps involving quantum gravity, that explains what happens inside. But for now, the singularity remains one of the greatest mysteries in science. Another fascinating part of how black holes work is their effect on time and space. The closer you get to the event horizon, the slower time passes relative to an outside observer. This isn't science fiction, it's a real prediction of relativity, confirmed by experiments in weaker gravitational fields. Near a black hole, time dilation becomes extreme. To someone falling in, their journey might seem quick, but to a distant observer, they would appear to freeze at the edge, their light stretched and faded as they approach the event horizon. It's important to note that black holes aren't cosmic vacuum cleaners sucking up everything indiscriminately. Their gravitational influence is no different from any other object of the same mass. If you replace the Sun with a black hole of equal mass, Earth would continue to orbit as usual, darkness instead of daylight, but no sudden plunge into oblivion. It's only if you venture too close to the event horizon that the point of no return seals your fate. Around black holes, physics becomes beautifully dramatic. Gas, dust, and even whole stars can get caught in the pull and spiral inward. As they fall, they form an accretion disk, heating up to millions of degrees and emitting intense radiation before vanishing forever. Magnetic fields twist and snap, generating powerful jets that can shoot material out at near-light speeds, sometimes for thousands of light years. Paradoxically, though black holes trap light, the regions just outside them can become some of the brightest places in the universe. So, in simple terms, a black hole is mass compressed into a region so dense that the escape velocity exceeds the speed of light. It is the most extreme outcome of gravity, where matter collapses under its own weight and space-time is curved to the breaking point. For Sagittarius A, it means 4 million suns worth of matter has been crushed into a gravitational abyss only about as wide as Mercury's orbit, silently shaping the destiny of the entire Milky Way. When we talk about Sagittarius A, the numbers can feel so overwhelming that they lose their meaning. 4 million times the mass of the Sun, 26,000 light-years away. These are facts, but they're hard to visualize. To really grasp what kind of monster we're dealing with, it helps to shrink things down to familiar scales. That's where comparisons become powerful, because they transform raw numbers into mental pictures. Let's start with the event horizon, the boundary beyond which nothing can escape. For Sagittarius A, the event horizon is about 25 million kilometers across. That sounds enormous, and it is, but let's put it into perspective. That's roughly the size of the orbit of Mercury, the innermost planet of our solar system. If you could somehow place Sagittarius A where our Sun is, its event horizon would swallow Mercury's orbit entirely. Venus and Earth, however, would remain safely outside of it. Think about that. Something that holds 4 million suns worth of mass could be contained within the orbital path of just the smallest planet in our solar system. Now compare that to the Sun itself. Our star has a diameter of about 1.4 million kilometers. Sagittarius A's event horizon is about 18 times wider than the Sun. In other words, if you lined up nearly 20 suns side by side, they would stretch across the black hole's shadow. That's massive, but when you consider that it's holding the weight of 4 million suns, the compactness becomes mind-bending. Let's bring Earth into the picture. Our planet's diameter is about 12,700 kilometers. You could fit Earth into Sagittarius A's event horizon more than 2,000 times across. Or imagine stacking Earths like marbles. You could drop millions upon millions of Earths into that volume and still not come close to matching its mass. It's a reminder of how tiny we really are compared to the scale of galactic structures. For a more human comparison, consider this. A commercial airplane travels around 900 kilometers per hour. If you try to fly around the event horizon of Sagittarius A at that speed, it would take you more than 3 years of non-stop flying to make a single lap. Light itself, the fastest thing in the universe, takes about 83 seconds to cross the diameter of the event horizon. That's less than a minute and a half for light to travel across a black hole that contains millions of suns. It's an object that is both staggeringly huge and frighteningly compact at the same time. Now let's widen the lens and compare Sagittarius A with other famous black holes. The black hole at the center of the galaxy M87, known as M87, has an event horizon so large that it could encompass our entire solar system out past Pluto. M87 is about 1,500 times larger than Sagittarius A. This contrast shows how Sagittarius A, while supermassive, is actually on the smaller side of the supermassive black hole family. Yet despite being relatively small, it still dwarfs anything we experience in the solar system. If you want another everyday analogy, picture the black hole scaled down to the size of a basketball. On that scale, the Sun would be smaller than a grain of sand orbiting at a distance of several meters. The Earth would be microscopic, practically invisible. That's how extreme the difference in density is, how much mass is packed into such a tight region. But here's the kicker: if you replace the Sun with Sagittarius A in our solar system, keeping the same distance between Earth and the central object, our orbit wouldn't change. We'd keep circling just as before. The only difference is that we'd be orbiting a dark void the size of Mercury's orbit instead of a shining star. That's the deceptive part of black holes. They're monstrous in scale, yet their gravity behaves just like any other object of the same mass, unless you get too close. So when you look up at the night sky, the stars seem peaceful, even delicate. But sitting at the center of it all is a gravitational abyss whose size rivals planetary orbits. Sagittarius A is proof that the universe operates on scales that dwarf human imagination. It takes something as wide as an entire planet's orbit and fills it with a darkness so complete that not even light can escape. And yet, it fits neatly into the heart of our galaxy, silently holding it together like the hub of an invisible wheel. Gravity is something we live with every day. It's what keeps us on the ground, what guides the planets in their orbits, what makes apples fall from trees. But around Sagittarius A, gravity isn't just a gentle tug. It's an overwhelming force that bends reality itself. To truly appreciate what's happening near this supermassive black hole, we need to shift our perspective from Newton's simple picture of gravity as a pull, to Einstein's profound idea of gravity as the warping of space and time. Einstein's general relativity tells us that mass and energy shape the fabric of the universe. Imagine space-time as a stretched sheet of rubber. Place a bowling ball on it, and the sheet curves. A marble rolled nearby will spiral inward, not because the ball is pulling it directly, but because the marble is following the curved path of the sheet. Now, replace the bowling ball with Sagittarius A, 4 million suns compressed into a region smaller than our solar system. The fabric of space-time doesn't just curve. It plunges into a chasm so steep that nothing, not even light, can climb back out. That chasm is the black hole. The closer you get to Sagittarius A, the more extreme this warping becomes. Stars that wander near the center of the galaxy aren't moving in straight lines through space. They're sliding along curved tracks carved by the black hole's gravity. We've seen this directly with stars like S2, which loops around Sagittarius A at incredible speeds. These stars are essentially test particles, tracing the invisible geometry of warped spacetime. Their dizzying orbits are living proof of the black hole's gravitational dominance. But Sagittarius A doesn't just bend space. It bends time. This is one of the strangest and most mind-bending consequences of relativity. Imagine you had a clock strapped to a spaceship orbiting near the black hole. From your perspective aboard the ship, time would seem to tick normally. But if someone watched your clock from far away, they would see it running more slowly than their own. This phenomenon is called gravitational time dilation. Near Sagittarius A, the effect is dramatic. The deeper you go into the gravity well, the slower your time runs compared to the rest of the universe. This isn't just theory, it's been observed. When star S2 made its closest approach to Sagittarius A in 2018, astronomers detected a redshift in its light caused by the stretching of spacetime itself. The star's clock, in effect, was running more slowly than our own. This was the first time such an effect had been measured so clearly near a supermassive black hole, and it was a direct victory for Einstein's theory. Sagittarius A isn't just a curiosity, it's a cosmic laboratory where we can test the very foundations of physics. The warping of spacetime also creates spectacular visual effects. If you could somehow survive near the black hole and look outward, the stars around you would appear distorted, their light bent into arcs and rings by the black hole's gravitational lensing. You might see the same star multiple times in different places. Light from behind the black hole would wrap around, creating a glowing ring, the photon sphere. These bizarre visual tricks aren't science fiction. They're a direct consequence of gravity so intense that even light is forced to obey its curves. Then there's the tidal force, the stretching caused by the difference in gravity between 2 points. On Earth, tidal forces from the Moon pull on our oceans, creating tides. Near Sagittarius A, tidal forces can tear stars apart. If a star strays too close, the side nearer the black hole feels a stronger pull than the far side. The star stretches, elongates, and can eventually be ripped into streams of gas. This process, called spaghettification, is one of the most violent displays of gravity at work. Matter doesn't just fall into Sagittarius A, it can be shredded, heated, and flung outward in bursts of energy before crossing the event horizon. Despite its power, Sagittarius A isn't constantly devouring everything around it. Most stars in the galactic center orbit safely at distances where the tidal forces, while strong, don't destroy them. The black hole is more like a massive sun at the galactic core, governing the orbits of its neighbors through its immense gravitational field. But make no mistake, cross the invisible boundary of the event horizon, and gravity becomes absolute. Inside, space and time collapse into a singular destiny, toward the center, with no escape possible. The intensity of Sagittarius A's gravitational pull reminds us of the scale of forces that shape the cosmos. Here on Earth, we think of gravity as weak, we can lift objects against it with ease, and even magnetic forces can overcome it. But on the grandest scales, gravity is the architect of galaxies, the sculptor of cosmic structures, and in the case of Sagittarius A, the keeper of the Milky Way's heart. It bends not just the paths of stars, but the very flow of time itself. When we picture a black hole, we often imagine a perfectly dark sphere swallowing anything that dares to cross its boundary. But the truth is that the regions around black holes can be some of the brightest, most energetic environments in the universe. The key to this paradox lies in the accretion disk, the swirling maelstrom of matter that spirals inward toward the event horizon of a black hole. For Sagittarius A, this disk is the glowing, turbulent region where the raw power of gravity reveals itself in spectacular ways. So what exactly is an accretion disk? Imagine space near Sagittarius A as a chaotic arena. Gas clouds, dust, and even unlucky stars drift through the galactic center. When this material comes under the black hole's gravitational influence, it doesn't fall straight in like a rock dropping into a pit. Instead, because the gas has angular momentum, it begins to spiral around, much like water circling a drain. As it does so, the particles rub against each other, creating immense friction. This friction, combined with gravitational compression, heats the gas to millions of degrees. And when gas reaches those temperatures, it glows, emitting light not just in visible wavelengths, but across the entire electromagnetic spectrum, from radio waves to X-rays. For Sagittarius A, this glowing disk is relatively faint compared to more active black holes, but it's still bright enough for us to study. Most of its energy radiates in radio waves, which is why the Event Horizon Telescope was able to image it. In visible light, Sagittarius A is hidden behind clouds of interstellar dust, but in radio and infrared, its glow cuts through the obscuring veil, allowing astronomers to peer closer than ever before into the Milky Way's heart. Now, picture the physics at play inside the disk. As gas spirals inward, it doesn't all fall in smoothly. Turbulent eddies form, magnetic fields twist and snap, and shockwaves ripple through the material. In fact, magnetic turbulence is thought to be the main driver of angular momentum transfer, allowing gas to spiral inward at all. Without this process, matter would just orbit endlessly around the black hole like planets do around the sun. Instead, magnetic instabilities act like a cosmic brake, bleeding off energy and letting gas sink deeper and deeper into the gravitational well. The inner edge of the accretion disk sits dangerously close to the event horizon, at a distance known as the innermost stable circular orbit, ISCO. For Sagittarius A, this orbit lies only a few times the size of the event horizon itself. Once matter crosses inside that radius, there are no stable paths left, it must plunge directly into the abyss. But just before that final plunge, the gas reaches its hottest, brightest state, radiating energy with almost reckless intensity. What's fascinating is that accretion disks are among the most efficient engines in the universe. A typical nuclear fusion reaction inside stars, like the ones powering our Sun, converts about 0.7% of mass into energy. Accretion around black holes can convert up to 40% of the infalling matter's mass into radiation. That's orders of magnitude more efficient than any process humans have ever devised. It's no wonder that the brightest quasars in the universe, distant galaxies lit up by actively feeding black holes, outshine entire galaxies of stars. Sagittarius A, however, is a quieter eater. Its accretion disk is dim compared to those of active galactic nuclei. This means that while gas and dust occasionally spiral in and light it up, the black hole spends much of its time relatively dormant. Astronomers describe Sagittarius A as a low-luminosity active galactic nucleus. It has the potential for incredible violence, but most of the time, it simply glows faintly, flickering now and then as bits of gas fall in. Still, even in its quiet state, the accretion disk of Sagittarius A is dynamic and unpredictable. Observatories like Chandra and XMM Newton have detected sudden flares of X-ray light from the disk, likely caused by magnetic reconnect ion events, moments when tangled magnetic fields snap and release massive bursts of energy. These flares are like lightning strikes in the cosmic storm, brief but brilliant reminders that the environment around the black hole is anything but calm. And if you could somehow hover near the accretion disk, the view would be surreal. Because of gravitational lensing, the glowing ring of gas would appear distorted, bent into arcs and halos around the black hole. The far side of the disk would be visible above and below the black hole as light wraps around the warped space. What you'd see is not a flat disk at all, but a strange, almost spherical glow surrounding the dark shadow at the center. This is exactly the kind of image captured by the Event Horizon Telescope, a glowing ring of gas encircling a black void. In short, the accretion disk of Sagittarius A is the stage where gravity, magnetism, and motion collide. It's where ordinary gas is transformed into radiant energy, where turbulence becomes visible light, and where the black hole's appetite briefly illuminates the surrounding darkness. Though Sagittarius A is currently a subdued eater, its accretion disk remains a reminder of the raw power that lurks at the heart of our galaxy, a power that can turn invisible gravity into visible fire. When the Event Horizon Telescope unveiled its first image of Sagittarius A in 2022, many people expected to see something as crisp and dramatic as the image of M87's black hole from 2019. Instead, what we got looked blurry, almost like a fuzzy orange donut smeared across space. But that fuzziness isn't a flaw in the telescope or a shortcoming of human ingenuity. It's a direct consequence of the messy, chaotic environment surrounding Sagittarius A and the extreme challenges of peering into the galactic core. Let's start with the obvious obstacle, the journey of light itself. Sagittarius A is about 26,000 light-years away from Earth. That means any light or radiation we detect has traveled through a vast swath of the Milky Way, encountering countless obstacles along the way. Interstellar gas and dust scatter and absorb light, especially in visible wavelengths. This is why, if you look toward the constellation Sagittarius in the night sky, you don't actually see the black hole itself. You see dense star fields and dark dust lanes obscuring the galactic center. To overcome this, astronomers rely on radio waves, which can cut through the dust more effectively. But even radio waves get distorted, blurred, and bent by the turbulent interstellar medium, much like light twinkling as it passes through Earth's atmosphere. Now, even once we filter through that cosmic fog, there's another problem. Sagittarius A is a restless and variable black hole. Unlike M87's giant, which is about 1,500 times more massive and relatively stable, Sagittarius A is small enough that matter orbits around it very quickly. Remember, its event horizon is about the size of Mercury's orbit. Gas swirling near that horizon can complete a full circuit in just minutes to hours. That means by the time astronomers try to take a snapshot of Sagittarius A, the accretion disk has already morphed, shifted, and flared. Imagine trying to photograph a campfire with a long exposure. The flames dance and flicker too quickly to produce a sharp, steady image. The result is a blur, not because the camera is faulty, but because the subject itself refuses to sit still. This variability is actually one of Sagittarius A's most fascinating features. The black hole doesn't consume matter in a steady stream. Instead, it gulps in irregular bursts. Gas clumps fall inward, magnetic fields reconnect, and flares erupt suddenly. These bursts of energy can change the brightness of the region dramatically in just minutes. For astronomers trying to stitch together an image from radio data collected across the globe, this variability is like trying to photograph a person who won't stop moving during the exposure. The fuzziness we see in the final image is, in part, a reflection of the black hole's own restlessness. On top of that, there's the sheer technical challenge of imaging something so distant and compact. The Event Horizon Telescope works by linking radio observatories around the world into a virtual Earth-sized telescope using a technique called Very Long Baseline Interferometry, VLBI. This method achieves resolution sharp enough to see details as small as a golf ball on the moon. But the data collected is incredibly sparse and noisy. To reconstruct an image, astronomers must run complex algorithms, filling in missing data and correcting for distortions. The process is like piecing together a jigsaw puzzle with most of the pieces missing and some bent out of shape. The final product is not a perfect photograph, but the best statistical reconstruction of what's really there. The fuzziness also tells us something important about Sagittarius A's environment. The radio emission we detect isn't just from gas right at the edge of the event horizon. It's also influenced by hotter plasma further out, magnetic fields, and even scattering in the interstellar medium between us and the black hole. That means the fuzzy ring is partly a composite of multiple layers of complexity, all projected onto our telescopes. And here's the mind-bending part: even though the image looks blurry, it's still a triumph of precision. That fuzziness contains rich scientific information. The width of the ring, its brightness, and even its irregularities match predictions from Einstein's general relativity. The blur isn't random, it's the fingerprint of warped spacetime combined with turbulent plasma physics, written across 26,000 light-years and captured by a network of telescopes spanning the globe. So while Sagittarius A may not give us the postcard-perfect clarity we dream of, its fuzziness is exactly what makes it so fascinating. It's a black hole wrapped in layers of dust, shrouded by plasma, and flickering unpredictably with bursts of energy. In other words, it's alive with cosmic drama. Every smear of that image is a story of gas colliding, magnetic field snapping, and light struggling to escape the gravitational abyss. The fuzziness isn't a flaw. It's the truth. It's what it looks like when you stare across tens of thousands of years, through interstellar fog, and into the heart of a galaxy at an object that bends reality itself. And perhaps, in its blur, we're reminded that the universe is not static or simple. It's turbulent, messy, and dynamic, just like the glowing ring of Sagittarius A. When most of us think about observing the universe, we picture telescopes gathering visible light, the same kind of light our eyes detect. We imagine peering through a telescope and seeing planets, stars, or galaxies shining in the night sky. But when it comes to Sagittarius A, that approach simply doesn't work. If you tried to see it in visible light, you'd be staring straight into a wall of cosmic dust and gas. The galactic center is cloaked by interstellar material so thick that visible light can't penetrate it. It's like trying to shine a flashlight through a mountain of smoke. You just won't see what's hiding behind it. That's why Sagittarius A reveals itself not in visible light, but in radio waves. Radio waves are much longer in wavelength than visible light, which allows them to slip past dust grains and gas clouds with relative ease. Where visible light gets scattered, absorbed, and blocked, radio waves thread their way through, carrying information across tens of thousands of light-years until they finally reach our telescopes on Earth. If we want to uncover the hidden heart of the Milky Way, we have to trade optical telescopes for radio observatories. And this is where Sagittarius A truly shines, literally. Despite being relatively dim compared to the blazing powerhouses of active galactic nuclei, Sagittarius A emits a steady glow in the radio spectrum. This glow comes primarily from hot, magnetized plasma swirling around the black hole. As electrons spiral along twisted magnetic field lines at near-light speeds, they emit what's called synchrotron radiation. This process is incredibly efficient at producing radio waves, making the galactic center a beacon in radio astronomy, even when it appears completely invisible in ordinary starlight. This radio brilliance is precisely why the Event Horizon Telescope, EHT, chose to observe Sagittarius A at a wavelength of 1.3 millimeters, a sweet spot in the electromagnetic spectrum. At this wavelength, The radio waves are long enough to pass through interstellar dust, but short enough to reveal incredibly fine detail, sharp enough to resolve the shadow of the black hole itself against the glowing background of its accretion disk. Without radio astronomy, we would have no direct image of Sagittarius A, no glimpse of the glowing ring surrounding the abyss. But the story doesn't stop there. Radio observations have revealed that Sagittarius A is far from quiet. Sometimes, its radio emission brightens in sudden bursts, echoing the flares seen in X-rays. These events might be caused by blobs of hot gas orbiting close to the event horizon or magnetic fields snapping and releasing energy. The flares often appear as brief, dramatic spikes in brightness, lasting minutes to hours. They're like whispers from the black hole, little outbursts reminding us that even in its current quiet state, Sagittarius A is still unpredictable and active. Radio astronomy has also allowed us to study the structure of the galactic center in ways no optical telescope ever could. With instruments like the Very Large Array, VLA, in New Mexico, the Atacama Large Millimeter Submillimeter Array, ALMA, in Chile, and others, astronomers have mapped the surrounding region in exquisite detail. They found threads of magnetized gas, shock fronts, and arcs of material all influenced by the gravitational and magnetic power of Sagittarius A. In fact, some of the strangest cosmic structures ever discovered, filamentary radio structures stretching light years across, lie in the galactic center, hinting at the dynamic forces at play around the black hole. One of the most fascinating aspects of Sagittarius A's radio glow is that it acts as a window into physics we cannot replicate on Earth. The plasma around the black hole is so hot and so extreme that it pushes our understanding of how matter and energy behave under intense gravity. By analyzing the radio waves, astronomers can probe the density of the plasma, the strength of the magnetic fields, and even the speed of gas orbiting near the event horizon. In other words, every bit of fuzz in those radio images is packed with data that helps us test Einstein's theories and refine our models of black hole behavior. It's almost poetic to think about it. Here is an object utterly invisible in the light our eyes can see, hidden behind 26,000 light years of dust, yet it blazes like a beacon in radio waves. What seems dark to us is, in fact, bright in another wavelength, if only we learn how to look. That's the magic of multi-wavelength astronomy, unlocking views of the universe our senses alone would never allow. So, while Sagittarius A might not dazzle in the night sky like a star, it is one of the most studied radio sources in the entire cosmos. Its hum at millimeter wavelengths has become our lifeline to understanding the invisible forces shaping the core of our galaxy. If visible light blinds us to its presence, radio waves are the translator, letting us listen in on the black hole's ongoing conversation with the universe. When people think of black holes, the image that often comes to mind is of an insatiable monster endlessly devouring everything in sight. Stars, planets, entire solar systems. And while some black holes truly live up to that terrifying reputation, Sagittarius A does not. In fact, compared to the ravenous engines at the cores of distant galaxies, our own central black hole is almost lazy. It's not eating much at all. To understand this, we need to compare Sagittarius A with its more active cousins, the so-called active galactic nuclei, AGN. These are galaxies where the central black hole is feasting so aggressively on its surroundings that the process unleashes staggering amounts of energy. In AGN, gas streams toward the black hole in dense flows, forming brilliant, blazing accretion disks that shine more brightly than the billions of stars in the host galaxy combined. Some even launch enormous jets of charged particles thousands of light-years into space. Quasars, the most luminous kind of AGN, can outshine entire galaxy clusters. By contrast, Sagittarius A is subdued. Despite its mass, about 4 million times that of the Sun, it barely sips from its cosmic surroundings. Astronomers estimate that Sagittarius A currently consumes only about the equivalent of the mass of the Moon every few thousand years. That's vanishingly small compared to the banquet AGN enjoy. Instead of a blinding quasar, our galactic center is classified as a low-luminosity AGN, a faint ember compared to the blazing furnaces of the cosmic deep. Why so quiet? A big part of the answer lies in fuel supply. For a black hole to shine as an AGN, it needs a steady flow of gas and dust funneling toward it. But the central region of the Milky Way, while rich in stars, doesn't currently deliver much material directly into Sagittarius A's grasp. Gas clouds do wander near from time to time, and when they do, The black hole puts on a brief show of flares and X-ray bursts. But overall, the streams of matter are thin and sporadic. The result is a black hole that spends more time waiting than eating. Another reason has to do with efficiency of capture. Even when gas does approach Sagittarius A, much of it doesn't make it all the way in. Magnetic fields, turbulence, and chaotic orbital paths often sling material back outward instead of letting it spiral across the event horizon. This means Sagittarius A loses a lot of potential food before it can consume it. Some studies suggest that more than 99% of the gas drifting inward never actually falls in. It gets heated and blown away instead. The little that does cross the boundary is just enough to keep the black hole faintly glowing, but not enough to power a galactic-scale light show. This relative dormancy is both a blessing and a puzzle. On the one hand, it makes our galactic environment far more hospitable. If Sagittarius A were an active quasar, Earth might not even be capable of supporting life. The radiation streaming from the galactic center could bathe the galaxy in lethal doses of X-rays and gamma rays, sterilizing planets and stripping atmospheres. Instead, we're fortunate to live in a galaxy where the central black hole is napping rather than raging. On the other hand, astronomers are deeply curious about why Sagittarius A is so quiet now. Evidence suggests it wasn't always this way. X-ray echoes bouncing off clouds near the galactic center, along with giant bubbles of gamma-ray emission known as the Fermi bubbles, hint that Sagittarius A was once far more active, possibly as recently as a few million years ago. Back then, it may have blazed like a true AGN, briefly turning the Milky Way into a miniature quasar. Why it quieted down remains an open question, but it's clear that black holes go through feeding cycles, with long periods of calm punctuated by bursts of intense activity. What's remarkable is that Sagittarius A's quiet state doesn't make it less interesting. In fact, its low-level activity provides a unique scientific opportunity. Most quasars are so bright that their surrounding environments are drowned in light, making it hard to study the finer details of black hole physics. But Sagittarius A, with its flickering, modest glow, is accessible. It allows astronomers to peer more carefully at processes like gas infall, magnetic turbulence, and flare production in a regime where things happen slowly enough to track in real time. So, far from being boring, Sagittarius A's subdued appetite is exactly what makes it such a valuable laboratory. It's like catching a wild predator not at full sprint, but at rest, quiet enough that we can study its muscles, its breathing, its heartbeat. From our perspective, it's almost the perfect black hole, dangerous in principle, but tame enough to observe safely, teaching us lessons about cosmic monsters without threatening our galactic neighborhood. Sagittarius A may not be devouring galaxies worth of matter, but in its restraint, it reveals a deeper truth. Black holes are not always raging furnaces. Sometimes, they are silent guardians, shaping their surroundings with a whisper rather than a roar. Today, Sagittarius A may seem like a sleeping giant, quiet, faint, and barely nibbling at scraps of gas drifting too close. But cosmic archaeology tells us that this calm exterior hides a far more dramatic past. The black hole at the center of our galaxy hasn't always been so subdued. In fact, the evidence suggests that Sagittarius A once roared with energy, sending shockwaves across tens of thousands of light-years. And the clues to this violent history come in the form of X-ray echoes and the vast Fermi bubbles ballooning above and below the galactic plane. Let's start with the X-ray echoes. Imagine a thunderstorm. The lightning strikes first, and the thunder rolls seconds later as the sound waves bounce off the landscape. Something similar happens on a galactic scale. When Sagittarius A produces a powerful burst of energy, say, an X-ray flare from a sudden feeding event, that light doesn't just travel in one direction. It spreads outward, bouncing off dense gas clouds near the galactic center. Because these clouds sit at different distances from the black hole, the reflections don't reach Earth all at once. Instead, we see echoes of long-past outbursts trickling in, like light delayed by the galaxy's structure. Over the last couple of decades, telescopes like Chandra X-ray Observatory and XMM Newton have detected these echoes. What they reveal is that Sagittarius A was far more active just a few hundred years ago. In fact, astronomers believe that around the 17th or 18th century, long before modern instruments existed, the black hole may have flared to a brightness 1,000,000 times stronger than what we see today. If humanity had radio telescopes at the time, the center of the galaxy might have looked like a beacon. By mapping these echoes, Scientists are effectively reconstructing the black hole's diary, piecing together a record of tantrums we missed before our age of technology. But the real showpiece of Sagittarius A's past is painted on a much larger canvas, the Fermi bubbles. Discovered in 2010 by NASA's Fermi Gamma Ray Space Telescope, these colossal lobes of high-energy emission extend about 25,000 light-years above and below the galactic plane. To put that in perspective, if the Milky Way was shrunk down to the size of a dinner plate, the Fermi bubbles would jut out taller than a skyscraper. They glow faintly in gamma rays, the most energetic form of light, and they're impossible to explain without a dramatic release of energy from the galaxy's core. So where did they come from? The leading theory is that a few million years ago, Sagittarius A went through an active feeding phase. Perhaps a large gas cloud or even a star wandered too close, spilling its guts into the accretion disk. As the black hole consumed the material, it blasted some of the energy back outward, inflating enormous bubbles of hot plasma that are still visible today. Another possibility is that a powerful starburst, an episode of intense star formation near the galactic center, fed energy into the region. But most evidence points towards Sagittarius A itself as the culprit, suggesting that our galaxy briefly lit up like a quasar before settling back into its current nap. The Fermi bubbles are more than just pretty structures, they are forensic evidence of black hole feedback, the process by which a central black hole influences its entire host galaxy. Even when a black hole isn't swallowing matter directly, the energy from past eruptions can stir and reshape galactic gas, regulating how stars form in the future. In this way, Sagittarius A acts like both a destroyer and a creator, blasting matter apart while also setting the conditions for new stars to be born. What's truly fascinating is the timescale. To us, a few million years feels impossibly long. But in cosmic terms, it's a blink of an eye. If Sagittarius A erupted just 2 or 3 million years ago, that means it was active when our early human ancestors were beginning to walk upright on the African savannas. The skies over Earth might have glowed faintly differently then, with extra radiation from the galactic core, though not strong enough to threaten us directly. We may be living in the quiet aftershock of a drama that unfolded during humanity's dawn. And here's the kicker, those outbursts might not be over. Astronomers watching Sagittarius A today see occasional hints of flaring, brief, sharp spikes in X-ray and radio light that suggest it still has the ability to wake up. Compared to the Fermi bubbles, these are small hiccups, but they remind us that a supermassive black hole is never truly dormant. It's more like a volcano, quiet for long stretches, but always capable of eruption. The combination of X-ray echoes and Fermi bubbles gives us a layered history of Sagittarius A's activity. The echoes tell us about recent centuries, the black hole's flickers in human historical time. The bubbles tell us about million-year timescales, long before recorded history. Together, they show that Sagittarius A is not just a quiet recluse, it is a cosmic actor with cycles of fury and calm, a being whose moods shape the galaxy itself. So when we look at the faint radio glow of Sagittarius A today, we're seeing only its present self. Hidden all around are footprints of its past, whispers of the times when it blazed like a true galactic engine. And if history is any guide, there's every reason to believe it could flare back to life again. When you picture the center of the Milky Way, it might be tempting to imagine only darkness, a void defined by the overwhelming presence of Sagittarius A. But in reality, the galactic core is far from empty. It's teeming with stars, some of them moving at such dizzying speeds that they defy ordinary imagination. Entire star systems orbit this hidden giant, locked in a gravitational dance that reveals both the ferocity and the subtlety of the supermassive black hole's influence. The stars nearest to Sagittarius are live in a region astronomers call the nuclear star cluster. This is one of the densest stellar neighborhoods in the galaxy. To give you a sense of scale, near Earth, the closest star is about 4.2 light-years away. In the galactic center, you could find thousands of stars packed into just a single cubic light-year. Imagine the night sky not with a few thousand visible stars like we see today, but with dazzling points of light in every direction. So many, so close, that they might make the heavens glow as if it were perpetual twilight. That's the kind of environment orbiting Sagittarius A. But it's not just the density that's astounding, it's the motion. These stars whip around the black hole at extreme velocities, far beyond anything we see in the solar system. Some travel at thousands of kilometers per second. To compare, Earth orbits the Sun at about 30 kilometers per second. The fastest stars near Sagittarius A move more than 100 times faster than that. At those speeds, a trip from New York to Los Angeles would take less than a minute. The reason is simple. The gravitational pull of 4 million suns concentrated in one point demands orbits of immense speed to balance against being pulled straight in. This neighborhood of racing stars has been crucial for proving Sagittarius A's existence. In fact, astronomers have carefully tracked dozens of them for decades, using infrared telescopes to peer through the dust that obscures the galactic center. By mapping their elliptical paths, scientists can calculate not only their speeds but also the invisible mass they're orbiting. The results are clear. There is something compact and unimaginably massive at the center, and the only plausible explanation is a black hole. Interestingly, not all of these stars are ancient relics as you might expect near a black hole. Some are surprisingly young, just a few million years old. These paradox of youth stars raise fascinating questions. How could stars form in such a hostile environment, where tidal forces should tear apart gas clouds before they collapse into stars? One theory is that they didn't form there at all. They may have migrated inward as part of stellar clusters, their orbits eventually captured by Sagittarius A's pull. Another possibility is that under the extreme pressures and densities of the galactic center, star formation happens in unusual, accelerated ways that we don't yet fully understand. And then there are the hypervelocity stars, rare objects that may have once been part of binary star systems orbiting close to Sagittarius A. In some cases, the black hole's gravity tears these pairs apart. One star gets captured, whipped into a tighter orbit around the black hole, while the other is flung outward at breathtaking speeds, sometimes fast enough to escape the galaxy entirely. These runaway stars are literally ejected by the gravitational slingshot of the Milky Way's central monster. Observations of hypervelocity stars provide further indirect evidence of Sagittarius A's power and its role in shaping the galaxy's stellar population. It's also worth noting that the stars near Sagittarius A are not just silent traces of gravity. They experience extreme physical effects as well. Their orbits bring them through regions of intense radiation, turbulent magnetic fields, and interactions with hot gas streams swirling toward the black hole. These harsh conditions test the limits of stellar survival, and yet many stars endure, continuing their orbits undisturbed. Their resilience highlights just how robust stars can be, even in the most extreme corners of the universe. The overall picture is staggering. Instead of an empty, quiet abyss, the galactic center is a bustling cosmic metropolis, stars zipping around at breakneck speeds, some forming strange and unexpected families, others being tossed into the galactic wilderness. This dynamic environment provides us with a natural laboratory for physics. Each star is like a test particle, revealing the invisible geometry of space-time shaped by Sagittarius A. And perhaps the most awe-inspiring thought is this: if you could somehow travel to a vantage point just outside this stellar swarm, you'd see a night sky unlike anything imaginable. Stars would streak across the heavens in years or even months, rather than the slow millennia we're used to on Earth. It would be a cosmic ballet choreographed by the gravity of a monster, a reminder that the galaxy's heart is not a place of emptiness, but of frenetic life, speed, and energy. Among all the stars that orbit Sagittarius A, one has become the undisputed superstar of astronomy, S2. This single star has revolutionized our understanding of the Milky Way's central black hole, providing some of the most direct and compelling evidence that Sagittarius A truly exists. Its orbit is like a cosmic probe, tracing invisible curves in space-time, and every swing it takes around the galactic center brings scientists new insights into the nature of gravity itself. So, who is S2? It's a relatively massive star, about 15 times the mass of our Sun and roughly 7 times its radius. Despite living in such a chaotic region, S2 is bright, hot, and young, only a few million years old. On Earth, if you look toward the galactic center with ordinary eyes, you wouldn't be able to see S2 because of the dense clouds of dust blocking visible light. But with infrared telescopes, which can pierce through that veil, astronomers can track its movements with exquisite precision. And what they've seen over the last 3 decades is nothing short of breathtaking. S2 completes a full orbit around Sagittarius A in just 16 years. To put that in perspective, the Sun takes about 225 million years to circle the Milky Way. This means S2 is racing through space on a timescale short enough that astronomers can actually observe multiple full orbits within a human lifetime. That's incredibly rare in astrophysics, where most cosmic phenomena play out over spans longer than civilizations last. At its closest approach, called Pericenter, S2 swoops within just 120 astronomical units, AU, of Sagittarius A. That's about 3 times the distance between the Sun and Pluto. For a star to come that close to a 4 million solar mass black hole and survive is remarkable. And when it does, its speed skyrockets to around 7,650 kilometers per second. That's roughly 2.5% the speed of light, fast enough to travel from Earth to the Moon in under a minute. It's the ultimate roller coaster ride in the galaxy, a journey dictated by the grip of a monster. The beauty of S2's orbit is not just in the spectacle but in the science it unlocks. By precisely tracking the shape and timing of its path, astronomers have been able to calculate the mass of Sagittarius A with extraordinary accuracy. They can see how tightly curved S2's trajectory becomes near Pericenter, and from that curvature, they deduce the invisible object's gravitational pull. Every time S2 swings past, it's like a yardstick measuring the black hole's weight. Without S2, our knowledge of Sagittarius A would be far more speculative. But S2 does more than weigh the black hole, it also tests the very fabric of physics. In 2018, during its latest closest approach, astronomers observed S2's light being stretched by gravitational redshift. This is exactly what Einstein's theory of general relativity predicts. Light climbing out of a deep gravitational well loses energy, shifting to longer wavelengths. For the first time, scientists were able to confirm this effect in such an extreme environment, providing yet another triumph for relativity. S2 is essentially a cosmic laboratory where Einstein's ideas face their most stringent tests. What's also intriguing is how stable the system is despite such violence. One might expect that a star traveling so close to a black hole would eventually be torn apart. Yet S2 remains intact, orbit after orbit, proof of how precise the balance of forces is. Still, there's always the possibility that interactions with other stars, gas clouds, or unseen objects like smaller black holes could eventually alter its fate. In the galactic center, nothing is guaranteed to last forever. Astronomers continue to track S2 with unmatched dedication. Each new data point sharpens our picture of Sagittarius A, confirming its mass, refining its location, and probing the geometry of the spacetime around it. Future instruments, such as the Extremely Large Telescope, ELT, promise to measure its orbit with even finer detail, perhaps even detecting the subtle precession of its path caused by the warping of spacetime itself. That would be a direct signature of general relativity in action on a galactic scale. For the general public, S2 is an almost poetic symbol. It's like a lone dancer circling a silent partner we can't see, performing steps choreographed by gravity itself. Every turn, every acceleration, every burst of speed tells us a story about the invisible giant at the galaxy's heart. When we watch S2, we're not just watching a star, we're watching the hand of Sagittarius A, guiding, shaping, and holding its companion in an embrace that spans both time and theory. So, when you hear about Sagittarius A being proven, remember that proof has a name, S2. This star has risked everything, diving close to the edge of oblivion, and in doing so, it has given us the clearest picture yet of the black hole that binds the Milky Way together. Without S2, our knowledge would be far less certain. With it, we have a front-row seat to one of the most extraordinary dances in the universe. Time is something we experience so personally that it feels absolute. The ticking of a clock, the beating of a heart, the rhythm of day and night, these feel universal. Yet near Sagittarius A, time itself bends under the weight of gravity. It's not just a poetic metaphor, it's a literal prediction of Einstein's theory of general relativity. The stronger the gravity, the slower time flows. And near a supermassive black hole like Sagittarius A, that effect becomes dramatic enough to turn science fiction into observable reality. Let's start with the basics. According to relativity, mass warps the fabric of spacetime. The heavier the object, the deeper the gravitational well it creates. For us on Earth, the effect is tiny. A clock at sea level ticks more slowly than a clock on top of a mountain, because it's slightly deeper in Earth's gravity well, but the difference is only billionths of a second per day. Our planet simply doesn't have enough mass to make the effect noticeable in daily life. Now scale up to Sagittarius A. Here, the mass of 4 million suns is compressed into a region no bigger than Mercury's orbit. That means the gravitational well is so steep that time itself noticeably stretches and slows. If you could hover near the event horizon, every second you experienced would correspond to many seconds, or even minutes or hours, for someone far away from the black hole. To an outside observer, it would look like your clock was crawling, while to you, everything would feel normal. This isn't just theory. We've actually seen hints of it in action, thanks to stars like S2. When S2 swooped near its closest approach to Sagittarius A in 2018, astronomers observed its light being redshifted, its frequency stretched as it climbed out of the black hole's gravitational well. That redshift wasn't just a Doppler effect of motion. Part of it was due to time dilation. From our perspective on Earth, the star's clock was running slower. This was the first direct detection of relativistic effects in a star orbiting a supermassive black hole, a triumph that showed Einstein's predictions hold even under such extreme conditions. The implications are staggering. Imagine two astronauts, one orbiting very close to Sagittarius A, and the other watching from a safe distance, say 26,000 light-years away here on Earth. The astronaut near the black hole might experience just a few hours, but by the time they return, if they could somehow escape, their colleague would have aged decades, centuries, or even longer. It's the ultimate time machine, though tragically one way if you cross the event horizon. And it gets even stranger near the edge itself. From far away, an object falling towards Sagittarius A seems to slow down as it approaches the event horizon, moving slower and slower, its light stretched into redder and dimmer wavelengths. To the outside world, it never quite crosses the horizon, it just freezes, fading into invisibility. But from the falling object's perspective, it plunges straight through, reaching the point of no return in finite time. This dual perspective is one of the most mind-bending aspects of relativity. Time depends on where you stand. What makes Sagittarius A so special is that we can actually test these ideas in a way that was impossible just a few decades ago. With instruments like the Gravity Interferometer at the Very Large Telescope in Chile, astronomers can track stars orbiting the galactic center with precision so sharp that even tiny relativistic effects in their motion and timing can be detected. Each measurement confirms that Einstein's theory remains unbroken, even at the very edge of physics where gravity is most extreme. For us, the concept of time dilation also highlights just how alien the environment around Sagittarius A is. It's not just a place of crushing gravity and blazing radiation. It's a realm where the fundamental flow of time itself refuses to behave the way we expect. If you were standing at the core of the Milky Way, looking out, you'd see the universe's clocks ticking unnaturally fast. Meanwhile, from Earth, we'd see your time almost standing still. So when we speak of Sagittarius A as a cosmic laboratory, time dilation is one of its greatest experiments. It's a natural proving ground for relativity, demonstrating that space and time are not rigid backdrops but living, flexible dimensions shaped by mass and energy. And in this galactic heart, time itself is stretched thin, caught in the grip of gravity's hand. The thought of falling into Sagittarius A is both terrifying and mesmerizing. It feels like the ultimate what-if scenario, one that bridges the line between hard science and the most haunting corners of human imagination. So, let's walk through what would actually happen if a human, or even a spaceship, were unlucky enough to drift too close to this supermassive black hole. First, we need to understand the defining boundary, the event horizon. This is the point of no return. For Sagittarius A, the event horizon has a radius of about 12 million kilometers, a sphere surrounding the black hole within which escape is physically impossible. Once you cross that line, no matter how powerful your rockets or how fast you try to move, you cannot get out. Not even light, the fastest thing in the universe, can escape. From the outside, this means we can never see inside. To us, everything that falls in appears to vanish, frozen at the edge, fading into darkness. But what would you, as the falling traveler, experience? As you approach the event horizon, gravity's pull grows stronger and stronger. The closer you are, the more severe the difference in pull between your head and your feet. This is the process called spaghettification. If you fell feet first, your legs would be tugged downward with immense force, while your upper body would feel a weaker pull. That difference would stretch you out, elongating your body like a strand of spaghetti. At the same time, your sides would be squeezed inward because gravity is focusing everything toward the center. You wouldn't just be pulled apart, you'd be thinned out. For a stellar mass black hole, spaghettification happens long before you reach the event horizon. The smaller the black hole, the more violent the tidal forces near its boundary. But Sagittarius A is a supermassive black hole. Its event horizon is huge, so the gravitational gradient at that outer boundary is actually more gentle. In fact, if you fell in, you might cross the horizon without immediately being torn apart. You wouldn't even feel a dramatic bump at that boundary. Locally, it would seem like ordinary space. The real destruction comes later, as you get closer to the singularity at the core. The singularity is where the known laws of physics break down. All the mass of 4 million suns is compressed into an infinitely dense point. As you near it, tidal forces increase without limit. Eventually, no matter what, you would be stretched thinner and thinner until your atoms themselves were ripped apart. In theory, even the particles that make up your atoms would be swallowed into the singularity, where the very meaning of space and time ceases to function. From your perspective, the fall into Sagittarius A would happen quickly. You'd plunge through the horizon and continue toward the center in a finite amount of time. But from an outside observer's point of view, things look very different. To us, watching from Earth, you would appear to slow down as you neared the event horizon. Your image would grow dimmer and redder, your signals stretched by gravitational redshift, until you faded into nothingness. From our vantage point, you'd never actually cross the horizon. You'd be frozen there, suspended in time, a ghost at the edge of infinity. This duality is one of the most haunting aspects of black holes. From your point of view, your journey ends at the singularity. From our point of view, you're trapped forever on the brink, never quite gone but never returning either. It's a paradox created by relativity, one that still stirs debate about what information falling into a black hole truly means. Now, let's extend this thought to something larger, a spaceship, or even an entire star. The same fate awaits. Stars that wander too close can be shredded by tidal forces before they even cross the horizon. Their gas and plasma get pulled into long streams, glowing brightly as they spiral into the accretion disk. For smaller objects, like planets or unlucky humans, the destruction happens deeper in, but the principle is the same. The closer you fall, the more space-time itself funnels you toward an inevitable end. And yet, some theories suggest something even stranger. Quantum physics raises the possibility that information about what falls into a black hole may not truly be lost, but encoded somehow in the event horizon itself, a concept known as the holographic principle. If that's true, then your fall might not be the end of your story in the cosmic sense. Instead, every detail of your existence could, in some bizarre way, remain imprinted on the edge of Sagittarius A. But practically, for a human or a spaceship, falling into Sagittarius A means obliteration. No escape, no survival, no return. It's the ultimate one-way journey. And yet, thinking through this scenario forces us to confront the deepest mysteries of the universe. What happens inside a black hole? Do singularities really exist? Or does some new physics, not yet discovered, take over? In a way, asking what would happen if we fell in is more than just a grim thought experiment. It's a lens into the boundaries of knowledge itself, a place where relativity, quantum mechanics, and human curiosity all collide, spiraling into the unknown, just like anything unlucky enough to cross Sagittarius A's point of no return. When most people think of black holes, the image that comes to mind is one of destruction, an inescapable monster devouring everything nearby. But Sagittarius A, like other supermassive black holes, plays a far more complex and even constructive role in the life of a galaxy. Rather than being only cosmic killers, these giants are also central engines of cosmic recycling, shaping the Milky Way's history by both feeding on matter and, paradoxically, regulating how much material becomes available for future stars. At its core, a black hole grows by feeding. Gas clouds, dust, and even stars can be drawn toward Sagittarius A. When that matter spirals inward, it forms an accretion disk, glowing fiercely as it heats up through friction and gravitational compression. Some of this material makes the final plunge across the event horizon, adding mass to the black hole itself. But not everything gets eaten. Some of the infalling gas gets whipped up, accelerated, and blasted outward in colossal jets and winds. This process is like a galactic digestive system. The black hole consumes, transforms, and then expels energy and matter back into its environment. The recycling effect here is vital for galaxy evolution. These outflows can travel across vast distances, stirring up and heating the interstellar medium, the gas and dust that act as raw material for new stars. In some cases, the black hole's outbursts suppress star formation by blowing gas away, starving star-forming regions. In other cases, they can actually trigger star formation by compressing nearby clouds, giving them the density needed to collapse into stars. So the black hole is both a regulator and a catalyst, capable of quenching or igniting star birth depending on the circumstances. In the Milky Way, Sagittarius A is relatively quiet today, accreting only small amounts of material. But the evidence of its past meals shows how dramatic this recycling can be. The Fermi bubbles, two gigantic lobes of high-energy plasma stretching 25,000 light-years above and below the galactic plane, are thought to be relics of a massive outburst from Sagittarius A millions of years ago. These bubbles contain material energized and expelled by the black hole, lingering as enormous scars in the halo of the Milky Way. They remind us that Sagittarius A is not just a passive anchor at the galaxy's center, but a dynamic participant in shaping its structure. Another piece of evidence for cosmic recycling comes from the detection of X-ray echoes in the galactic center. These are reflections of past flares from Sagittarius A, bouncing off nearby clouds of gas. Such flares suggest that, at times, our black hole has been far more active, briefly turning into a miniature quasar, a beacon powerful enough to outshine all the stars of the Milky Way combined. During those phases, its ability to push and redistribute matter would have profoundly affected how the galaxy evolved. This recycling process also provides a kind of feedback loop. When Sagittarius A feeds too aggressively, its outbursts expel gas so violently that the black hole starves itself for a time, forcing a period of quiescence. When the environment cools and gas drifts back, feeding resumes, leading to another cycle of growth and expulsion. This self-regulation helps explain why galaxies and their central black holes appear to grow together. Observations across the universe show a clear relationship between the mass of a galaxy's central black hole and the properties of its bulge of stars. It's as though the black hole and the galaxy co-evolve, locked in a feedback dance spanning billions of years. On the largest scales, this recycling is one of the reasons galaxies don't just collapse into runaway star factories. Without the regulating influence of black holes, galaxies would burn through their gas too quickly, leaving them dead and dark long before their time. With black holes stirring and redistributing that gas, galaxies evolve more slowly, stretching their star-forming lifetimes across billions of years. So in a way, Sagittarius A is both destroyer and creator. Yes, it can shred stars, swallow planets, and warp space-time. But it also breathes life into the Milky Way, ensuring that gas doesn't just collapse all at once but cycles in and out of star formation. Without this balance, our galaxy, and maybe even our solar system, might look very different today. And that's the strange irony. A black hole, the very symbol of consumption, is also a giver of cosmic order. By feeding and blowing out matter, it shapes the ecosystem of stars, dust, and gas that makes galaxies vibrant. In the case of the Milky Way, Sagittarius A isn't just our central monster. It's also our galactic gardener, pruning, recycling, and tending the conditions for the galaxy's long-term survival. Whenever we talk about Sagittarius A, it's natural to wonder, should we be afraid of this cosmic monster sitting at the heart of our galaxy? After all, it's a supermassive black hole with the gravitational strength to warp space-time itself and swallow stars whole. The idea of such an object lurking in our galactic neighborhood might feel unsettling. But here's the reassuring truth: we're completely safe. Let's start with the basics of distance. Sagittarius A is located roughly 26,000 light-years away from Earth. To put that into perspective, 1 light-year is about 9.5 trillion kilometers. Multiply that by 26,000 and you get a number so huge it's nearly impossible to comprehend. This separation is vast, so vast that, despite Sagittarius A's incredible mass, its gravitational influence on our solar system is essentially negligible. The Sun, not Sagittarius A, is the dominant gravitational force in our lives. It keeps Earth and the other planets securely bound in their orbits. Another comforting fact is that Sagittarius A is not some roaming predator moving through the galaxy. It's fixed at the galactic center, anchored by the Milky Way's mass and structure. The Sun and all the other stars in our galaxy orbit around it, but on an enormous scale, taking hundreds of millions of years to complete just one galactic circuit. For Earth, that means Sagittarius A is not heading our way. It isn't drifting closer. It's simply sitting where it has been for billions of years, playing its role as the galaxy's central anchor. Some people imagine black holes as vacuum cleaners sucking up everything in sight. That's a misconception. Black holes don't pull in matter indiscriminately from vast distances. Their gravity works like any other objects. It just becomes extreme when you get close. If, hypothetically, our Sun were replaced by a black hole of the same mass, Earth would continue orbiting just as before. It would get cold and dark, but it wouldn't be pulled in. Likewise, Sagittarius A exerts no dangerous gravitational pull on us from where it sits. And what about radiation? Could its flares or past outbursts threaten Earth? Again, the sheer distance protects us. Even though Sagittarius A occasionally emits bursts of X-rays and gamma rays, by the time that radiation travels 26,000 light-years, it spreads so thinly that it poses no risk to our planet. Earth is far more affected by our own Sun's activity than by anything Sagittarius A produces. It's also worth remembering that Sagittarius A is quiet by cosmic standards. Many other galaxies host active galactic nuclei, where supermassive black holes blaze brightly as they devour vast amounts of material. These quasars can unleash torrents of radiation powerful enough to sterilize star systems nearby. Sagittarius A, however, is a relatively calm black hole. It nibbles rather than feasts, producing only occasional flares rather than constant, violent outbursts. So, in a very real sense, Sagittarius A is more of a background presence than a threat. It shapes the Milky Way on cosmic scales, regulating star formation and anchoring the galaxy's structure. But on the human scale, our daily lives, our solar system, it's a distant giant, too far away to touch us. In fact, we owe part of our existence to this very stability. If Sagittarius A were much closer, or if the Milky Way's black hole were hyperactive like those in some other galaxies, conditions might not have been favorable for life to develop here. The quiet distance of Sagittarius A has allowed Earth to enjoy billions of years of relative calm, long enough for life to evolve from microbes into complex organisms, and eventually into humans capable of looking back and studying the black hole itself. So, while it's fun, and a little chilling, to imagine what would happen if we fell into Sagittarius A, the reality is that we are safe. Our solar system is far outside the danger zone, securely orbiting the galaxy from a comfortable distance. We can admire, study, and even fear Sagittarius A in theory, but in practice, it poses no threat to us. If anything, it's a distant neighbor whose influence is more creative than destructive. The black hole at the Milky Way's core is a cosmic monster, yes, but it's a monster confined to its cage, a cage so far away that its claws can never reach us. Instead of worrying, we can focus on the wonder of what Sagittarius A teaches us. How galaxies grow, how black holes work, and how the universe recycles matter and energy across unimaginable spans of space and time. Though Sagittarius A is mostly quiet, every so often it makes its presence known in spectacular fashion. Astronomers who have studied the galactic center with sensitive instruments have occasionally caught brilliant flares of X-rays and infrared light erupting from near the event horizon. These flares, sudden bursts of energy, last anywhere from minutes to a few hours, and they provide rare glimpses into the extreme physics happening at the very edge of our galaxy's hidden giant. So what exactly are these flares? To put it simply, they're like hiccups of the black hole's accretion process. Normally, Sagittarius A sips rather than feasts. It accretes very little material compared to the monstrous quasars in other galaxies. But sometimes, a clump of gas or a fragment of matter gets too close, spiraling inward toward the event horizon. As it plunges into the gravitational grip of the black hole, it gets heated to millions of degrees, releasing energy in the form of X-rays and infrared radiation. To astronomers on Earth, this sudden heating appears as a spike in brightness, a flare. Detecting these events isn't easy. The galactic center is shrouded in thick clouds of dust and gas, making it opaque to visible light. That's why astronomers rely on telescopes tuned to other wavelengths, especially X-ray observatories like NASA's Chandra X-ray Observatory and infrared telescopes like the Very Large Telescope, VLT, in Chile or the Keck Observatory in Hawaii. These instruments can peer through the dust and capture fleeting changes in Sagittarius A's brightness. One of the most remarkable observations came in 2019, when astronomers recorded the brightest infrared flare ever seen from Sagittarius A. For a brief moment, the black hole shone 75 times brighter than its usual level. The cause was likely a blob of hot gas whipping around the event horizon at nearly the speed of light, glowing intensely before either being consumed or flung away. Events like this remind us that while Sagittarius A is calm on average, it still has a volatile streak. What makes these flares so scientifically valuable is that they act as probes of the environment near the event horizon. By measuring how quickly the flares rise and fade, astronomers can estimate how close the emitting material was to the black hole and how fast it was moving. In some cases, the flickering of the flare even reveals orbital motion, a hot spot of gas making a partial loop around the event horizon before vanishing. These real-time changes allow researchers to test general relativity under conditions that no laboratory on Earth could ever reproduce. The flares also raise fascinating questions. Are they caused by magnetic reconnect ion events, where tangled magnetic field lines snap and release energy, similar to solar flares on our Sun, but magnified to cosmic proportions? Or are they simply the result of clumps of gas plunging inward, shredded and superheated as they fall? The truth may be a combination of both, with Sagittarius A's magnetic fields playing a critical role in how matter accretes and occasionally erupts in dramatic fashion. These observations also connect to the broader mystery of why Sagittarius A is so underfed compared to other supermassive black holes. Each flare is a reminder that there is material orbiting dangerously close, sometimes falling in, sometimes just grazing the edge and whipping away. By studying the frequency and energy of these flares, scientists hope to understand the feeding habits of Sagittarius A, and, by extension, the quiet phases of other galaxies. For us here on Earth, these flares are harmless. The energy dissipates long before it reaches us across 26,000 light-years of space. But for astronomers, they are golden opportunities, fleeting windows into one of the most extreme environments in the universe. Every flare is like a cosmic heartbeat, a pulse from the Milky Way center reminding us that Sagittarius A, though quiet, is never fully asleep. And perhaps most importantly, these flares give us a way to watch the drama of matter versus gravity play out almost in real time. In the span of a human evening, we can observe material orbit, flare, and vanish near the edge of a black hole that has been shaping our galaxy for billions of years. It's a humbling connection between our fleeting human perspective and the vast timescales of the cosmos. One of the most dramatic demonstrations of Sagittarius A's power doesn't come from the occasional flare alone, but from larger encounters, events where entire gas clouds stray too close to the black hole and are torn apart in a cosmic tug-of-war. Among these, the most famous is the story of G2, a mysterious object that gave astronomers front-row seats to the spectacle of a black hole devouring matter on a much larger scale. G2 was first spotted in the early 2000s, glowing faintly in infrared light. Initially, astronomers thought it was just a compact cloud of hydrogen gas, drifting innocently near the galactic center. But as they tracked its orbit over the years, they realized it was headed straight towards Sagittarius A, on a dangerously close approach. The excitement in the astronomical community was enormous. For once, researchers weren't just speculating about what happens when a black hole consumes something, they had a chance to watch it unfold in real time. As G2 neared Pericenter, the closest point in its orbit around Sagittarius A, in 2014, telescopes across the world were trained on it. The cloud stretched and elongated, pulled like taffy by the intense gravity of the black hole. This is a perfect example of tidal forces, where gravity acts more strongly on one side of an object than the other, stretching it into a long filament. In effect, G2 was being spaghettified on a much larger scale than a single star or planet would be. But here's where things got interesting. Astronomers expected fireworks, huge flares, bursts of radiation, and signs of Sagittarius A feasting on the shredded remains of G2. Instead, what they saw was underwhelming. While G2 was indeed stretched and distorted, Sagittarius A didn't produce the enormous outburst many had predicted. The black hole seemed to absorb only a small amount of the material, and much of the cloud survived the close encounter, continuing on its orbit as a stretched, battered remnant. This anticlimax left scientists puzzled. Some began to suspect that G2 wasn't just a simple gas cloud after all. Perhaps at its core was a star, or even a pair of stars that had merged, shrouded in a thick envelope of gas and dust. That would explain why the object held together better than expected and why it didn't immediately vanish into Sagittarius A. In this interpretation, what we saw wasn't a cloud being eaten, but rather a star carrying a cloak of gas that got stripped during the encounter. Regardless of its true nature, the G2 event gave astronomers invaluable data about the environment around Sagittarius A. By watching how the cloud stretched and how its gas interacted with the black hole's surroundings, scientists could study the physics of accretion, magnetic fields, and the turbulent plasma near the event horizon. It showed that the feeding process of a black hole is not always straightforward. Sometimes the meal resists digestion. And G2 isn't the only story of its kind. Other gas clouds, filaments, and even entire star-forming clumps drift dangerously close to Sagittarius A. Each one provides another test case for how supermassive black holes interact with their environment. These encounters highlight the chaotic ecosystem of the galactic center, where gravity, radiation, and turbulence constantly battle for control. For us, these events serve as vivid reminders that while Sagittarius A is relatively quiet most of the time, it's always ready to interact with anything that comes too close. The fate of G2 illustrates just how complex and unpredictable these encounters can be, sometimes violent, sometimes anticlimactic, but always scientifically rich. And it underscores an important truth: black holes are not just passive voids. They are dynamic players, influencing their surroundings in ways that ripple outward across entire galaxies. The next time a gas cloud, star, or unlucky object strays too near Sagittarius A, we'll be watching again, waiting to see how our galaxy's hidden giant responds. Each event is a natural experiment in the most extreme physics the universe has to offer, reminding us that even in apparent quiet, the galactic center is alive with drama. When we think about Sagittarius A, it's tempting to imagine it as a solitary ruler of the Milky Way's core, sitting unchallenged at the galactic throne. But the truth is, the heart of a galaxy is a busy, chaotic environment, full of stars, stellar remnants, and even other black holes. And one of the most fascinating possibilities scientists are exploring is that Sagittarius A might someday merge with smaller black holes that wander too close. If and when that happens, the event wouldn't just reshape the galactic center, it would send gravitational waves rippling through the very fabric of spacetime itself. Gravitational waves are distortions in spacetime predicted by Albert Einstein's theory of general relativity over a century ago. They are produced when massive objects accelerate violently, such as during the collision of two black holes. Imagine throwing a stone into a still pond. The ripples that spread outward are like gravitational waves spreading across the universe, carrying information about their origin. The difference is that instead of water rippling, it's space and time themselves stretching and squeezing. In 2015, the LIGO Observatory detected gravitational waves directly for the first time, from the merger of two black holes far smaller than Sagittarius A. That discovery opened an entirely new era of astronomy, giving us a way to listen to the universe rather than just look at it. But what if we caught gravitational waves from something on the scale of Sagittarius A? The signal would be immense, a cosmic bass note reverberating across the universe. Now, Sagittarius A is not currently merging with another supermassive black hole, but astronomers suspect that throughout cosmic history, galaxies have collided and merged countless times. When two galaxies come together, their central black holes eventually sink to the center of the newly formed galaxy and spiral toward each other. If the Milky Way collides with another large galaxy, as it will with Andromeda in about 4 billion years, our central black hole may one day pair up with Andromeda's central black hole. That dance would culminate in a titanic merger, unleashing a burst of gravitational waves so powerful that detectors across the universe could pick it up. Even before such colossal events, Sagittarius A might occasionally merge with smaller black holes, those formed from the collapse of massive stars that orbit in the galactic center. When one of these stellar mass black holes drifts too close, it could be captured, orbit for a time, and eventually spiral inward due to the emission of gravitational waves. The final moments, as the smaller black hole is swallowed, would produce a distinctive signal called an extreme mass ratio in spiral, or EMRI. Detecting these events would give us unparalleled insight into the environment around Sagittarius A, as the orbit of the smaller black hole would trace out the spacetime geometry near the event horizon with exquisite detail. The technology to detect such subtle signals is on the horizon. While ground-based detectors like LIGO and Virgo are tuned to the higher frequency waves from smaller black hole mergers, future missions like the Laser Interferometer Space Antenna, LISA, a space-based observatory planned by the European Space Agency, will be sensitive to the lower frequency waves expected from mergers involving supermassive black holes. With LISA, we could one day hear the slow, deep rumble of Sagittarius A interacting with other black holes. Why does this matter? Because gravitational waves don't just tell us that a merger happened, they carry direct information about the masses, spins, and even the space-time environment of the colliding black holes. Detecting such waves from Sagittarius A would allow scientists to test Einstein's theory in the strongest gravitational fields possible, and perhaps even uncover new physics beyond relativity. And think about the grandeur of it. An event happening 26,000 light-years away could still shake the fabric of space-time here on Earth, ever so slightly. The effect on us would be tiny. Gravitational waves stretch and compress distances by less than the width of a proton. But with the right instruments, we can capture those ripples and decode the story of a cataclysmic collision in our galactic backyard. So, while Sagittarius A may seem quiet today, its future is full of possibilities. One day, it may merge with smaller companions, sending ripples across the universe. And billions of years from now, when the Milky Way and Andromeda finally collide, Sagittarius A could meet its match. In a dance of unimaginable violence and beauty, a union that would literally shake the cosmos. Sagittarius A isn't just an astronomical curiosity, it's a cosmic laboratory, a place where the laws of physics are pushed to their absolute limits. For over a century, Albert Einstein's theory of general relativity has served as our best description of gravity, space, and time. We've tested it in many ways, from observing how starlight bends around the Sun during an eclipse to watching the slow precession of Mercury's orbit. But if we want to see how relativity behaves in its most extreme environment, we have to look to black holes. And Sagittarius A is the perfect subject. At its heart, general relativity describes how mass and energy curve space-time, and how that curvature directs the motion of objects and even light itself. Near a supermassive black hole like Sagittarius A, space-time is warped so violently that everyday intuition collapses. Here, relativity doesn't just predict subtle shifts or slight bending of starlight, it predicts orbital paths twisted by gravity, clocks running at different speeds, and light struggling to escape. Studying these phenomena around Sagittarius A gives us the rare chance to confirm or challenge Einstein's ideas. One of the most direct tests comes from observing the orbits of stars near the black hole. The star S2, which we've already discussed, has been especially valuable. As it swings close to Sagittarius A every 16 years, astronomers have been able to measure the effect of gravitational redshift, a key prediction of relativity. Light from S2 stretches into longer, redder wavelengths as it climbs out of Sagittarius A's deep gravitational well. This isn't something Newtonian physics can explain. It's pure relativity in action, visible from 26,000 light-years away. Another test is the precession of S2's orbit. Instead of tracing a perfect ellipse, S2's orbit slowly rotates over time, creating a rosette-like pattern. This orbital precession, also seen in Mercury's path around the Sun but amplified here by millions of times, matches Einstein's equations with remarkable precision. Each measurement provides yet another confirmation that relativity holds, even under the crushing gravity of a supermassive black hole. Sagittarius A also allows us to study frame dragging, sometimes called the lens-thirring effect. If the black hole is spinning, as most astrophysicists believe, then its rotation should literally drag spacetime around with it. Matter orbiting close to the black hole would feel this effect, experiencing tiny but measurable changes in motion. Detecting frame dragging near Sagittarius A could give us direct information about the black hole's spin, a property notoriously difficult to measure. The 2022 image of Sagittarius A captured by the Event Horizon Telescope added another powerful tool to the physics toolkit. By mapping the shadow of the black hole against the glowing plasma around it, scientists could compare what they saw to the predictions of relativity. And the results? The shape and size of the shadow were exactly what Einstein's equations forecasted. It was one of the strongest confirmations yet that general relativity remains unbroken, even under conditions where it might be expected to fail. But here's where things get even more exciting. Sagittarius A also offers the chance to test relativity's limits. Physicists know that while Einstein's theory has been extraordinarily successful, it doesn't yet reconcile with quantum mechanics, the other great pillar of modern physics. At some scale, relativity should break down, or at least need modification. By studying extreme objects like Sagittarius A, we might find the first hints of those cracks. Tiny deviations in orbital paths, unexpected patterns in flares, or subtle irregularities in the black hole's shadow could all point toward new physics. Looking to the future, instruments like the Gravity Interferometer at the Very Large Telescope and upcoming space missions such as LISA will push these tests even further. They'll allow astronomers to track stars and compact objects with unprecedented precision, potentially catching effects too subtle for today's instruments. Each new dataset tightens the leash on Einstein's equations. So far, relativity keeps passing with flying colors, but the quest to probe deeper never ends. So when we say Sagittarius A is a natural laboratory, we mean it literally. Unlike a particle collider or a controlled experiment on Earth, this laboratory is written into the fabric of the universe itself. It's a place where nature has created the ultimate experiment in gravity, a massive black hole bending space and time so violently that no human-built device could ever reproduce it. By watching, measuring, and interpreting, we get to participate in this ongoing cosmic experiment. And perhaps the most humbling thought is this: the results we see today were written into the light 26,000 years ago, when it first began its journey from the galactic center. Every photon captured by our telescopes carries with it the imprint of relativity, proof that Einstein's vision continues to hold sway even at the heart of our galaxy. When we talk about Sagittarius A, it already feels enormous, for a million times the mass of the Sun, pulling entire star systems into its invisible grip. But in the cosmic zoo of black holes, Sagittarius A is actually modest. To really appreciate its place in the universe, we need to compare it with other giants, especially one of the most famous, M87's central black hole, known as M87. This monster is in a completely different league, roughly 1,500 times more massive than Sagittarius A. M87's black hole weighs in at about 6.5 billion solar masses. That's not just big, it's almost unfathomable. If Sagittarius A is like a mountain, M87 is an entire continent. Its event horizon, the boundary beyond which nothing can escape, spans about 40 billion kilometers, which is roughly the size of our entire solar system. By contrast, Sagittarius A's event horizon is only as wide as Mercury's orbit. In terms of scale, Sagittarius A is compact, a heavyweight packed into a relatively small volume, while M87 sprawls across vast distances. One of the reasons M87 is so famous is that it was the first black hole ever imaged directly by the Event Horizon Telescope in 2019. That iconic orange donut, the very first photograph of a black hole shadow, wasn't Sagittarius A, but M87, sitting 55 million light-years away in the Virgo cluster. Even though it's vastly farther than our own black hole, its sheer size made it easier to image. Sagittarius A's smaller scale and turbulent surroundings made its image fuzzier and harder to capture. Another striking difference lies in their activity levels. M87 is an active galactic nucleus, meaning it's consuming large amounts of material and blasting out radiation. One of its most dramatic features is a relativistic jet, a beam of charged particles shooting out from near the black hole at almost the speed of light. This jet extends 5,000 light-years into space, longer than the span of the entire Milky Way's disk thickness. It's a breathtaking example of how a black hole doesn't just swallow matter, it can also shape and energize entire galaxies with its output. Sagittarius A, by contrast, is a quiet eater. It sips on gas and dust, flaring occasionally, but it doesn't launch enormous jets or radiate at extreme levels. Yet, despite these differences, both black holes provide crucial insights into astrophysics. Sagittarius A allows us to study black holes up close since it's in our galactic backyard. We can track the motions of individual stars around it and test Einstein's relativity with unmatched precision. M87, on the other hand, shows us what happens when a supermassive black hole is in full throttle mode, dramatically influencing its galaxy and broadcasting its presence across intergalactic space. Together, they give us two ends of the spectrum, the quiet ruler and the roaring king. It's also fascinating to consider what their comparison says about cosmic history. How did Sagittarius A grow to only 4 million solar masses, while M87 ballooned into billions? Did M87 form earlier, gobbling up more matter during the universe's youth, while Sagittarius A had fewer opportunities to feed? Or are there fundamental differences in how galaxies evolve that set the stage for their central black holes? These are questions that still challenge astrophysicists, and studying both Sagittarius A and M87 side by side may hold the key to unlocking them. The sheer size difference also sparks the imagination. If you could replace Sagittarius A with M87's black hole, its event horizon would swallow up the orbits of all the inner planets and stretch nearly to Neptune. The night sky would look dramatically different, with powerful radiation and jets lighting up the galactic core. It's almost lucky that our galaxy hosts a relatively tame black hole rather than a behemoth like M87's. We get the scientific wonder without the existential danger. In the end, comparing Sagittarius A with M87 isn't just about marveling at numbers. It's about seeing the incredible variety of black holes in the universe. Some are modest giants, quietly influencing their surroundings, while others are cosmic engines, blazing with energy and reshaping galaxies on grand scales. Both, however, serve as windows into the same fundamental mysteries of gravity, space, and time. Sagittarius A shows us the details up close. M87 reveals the epic scale from afar. Together, they remind us that the universe doesn't deal in half measures. When it creates monsters, it creates them in every size imaginable. One of the most fascinating aspects of studying Sagittarius A and its kin is not just understanding how they behave now, but uncovering how they came to be in the first place. When astronomers peer deep into the universe, they're effectively looking back in time, because light from distant objects takes billions of years to reach us. And what they've found is startling. Supermassive black holes already existed when the universe was less than 1 billion years old. Some of them are even larger than M87, tipping the scales at tens of billions of solar masses. This raises a profound cosmic mystery. How could something so huge form so quickly? If black holes begin their lives as the collapsed cores of massive stars, objects perhaps 10 to 100 times the mass of the Sun, then growing into a monster billions of times the Sun's mass in under 1 billion years seems almost impossible with ordinary physics. Even if they fed continuously at the maximum rate allowed by physics, known as the Eddington limit, it would still take longer than the age of the early universe to reach those sizes. So scientists are left with a puzzle. Did the first black holes somehow start out much larger than stellar remnants? Could they have formed directly from enormous clouds of primordial gas collapsing under their own gravity, bypassing the star stage entirely? These so-called direct collapse black holes are one proposed solution. Instead of starting as a small seed and growing slowly, they might have been born already weighing 100,000 to 1 million solar masses. From there, with enough gas in the young, dense universe, they could rapidly bulk up into supermassive black holes. Another possibility is that the early universe was far more chaotic than we imagine, with galaxies colliding and merging at a furious pace. Each collision could funnel vast amounts of gas into the center, feeding the growing black holes. Faster than what we usually observe today. In this scenario, violent cosmic environments acted like accelerators, giving black holes the fuel they needed to reach their staggering sizes. Some theorists even suggest that primordial black holes, hypothetical black holes formed moments after the Big Bang itself, might have seeded the growth of supermassive black holes. If regions of the infant universe collapsed under their own density fluctuations, they could have created black holes long before the first stars even existed. Though this idea is still speculative, it would elegantly explain how supermassive black holes appeared so early, because they would have had a head start of hundreds of millions of years. Sagittarius A, being a relatively modest supermassive black hole, plays a role in this mystery as well. At 4 million solar masses, it's small compared to the giants of the early universe. Why didn't it grow as large as they did? Was it simply unlucky, living in a quieter part of cosmic real estate with fewer galaxy mergers to feed it? Or has it already gone through a period of rapid growth in the past, only to settle down once its environment ran out of fuel? The evidence of past outbursts, like femibubbles and X-ray echoes, suggests that Sagittarius A may have been much more active in the past. Adding to the puzzle, recent observations show that even dwarf galaxies, tiny compared to the Milky Way, can harbor surprisingly large black holes at their centers. This raises the question of whether the link between galaxy size and black hole size is as straightforward as we once believed. Perhaps black holes don't always grow in lockstep with their host galaxies. Maybe their growth depends on unpredictable factors, like local gas flows or the timing of mergers, rather than just overall galaxy mass. The mystery of supermassive black hole formation is not just an academic curiosity, it's deeply tied to the story of the universe itself. Black holes influence galaxy evolution, regulate star formation, and shape the cosmic web of structure. Understanding how they came to be so massive so early will shed light on the broader history of galaxies, including our own Milky Way. Future telescopes like the James Webb Space Telescope and upcoming next-generation observatories are already peering into the early universe, searching for the faint glimmers of the first galaxies and quasars. By finding and studying the youngest black holes, astronomers hope to piece together their origins. Did they start big? Did they grow fast? Or are we missing an entirely new piece of physics? At the heart of this mystery lies a humbling reminder. Even with all our knowledge of relativity, stellar evolution, and cosmic history, the universe still holds secrets beyond our grasp. Sagittarius A, M87, and their kin are not just endpoints of gravitational collapse. They're clues to a deeper, older story about how the cosmos built its largest structures in record time. Unlocking that story may reshape not only our understanding of black holes but also the very timeline of the universe's evolution. When we think of Sagittarius A, it's tempting to imagine it as a passive cosmic sinkhole, just sitting there at the center of the Milky Way, swallowing whatever happens to wander too close. But in reality, its role is far more dynamic. This supermassive black hole acts as a kind of cosmic regulator, subtly shaping the life cycle of stars and the overall health of our galaxy by controlling the flow of gas in its neighborhood. Gas is the raw material for stars. Wherever it collects in dense, cool clouds, new stars are born. The center of the Milky Way is rich in gas and dust, which should make it a stellar nursery bursting with new suns. Yet, the rate of star formation near Sagittarius A isn't as extreme as one might expect. Why? Because the black hole itself plays a hand in both nurturing and suppressing star birth. When gas falls towards Sagittarius A, it heats up, sometimes reaching millions of degrees, and releases tremendous amounts of energy. This radiation and outflow can push surrounding gas away, preventing it from cooling and condensing into stars. In this way, the black hole can quench star formation, acting almost like a galactic thermostat. Too much gas flowing in, and Sagittarius A releases a burst of energy that clears the region, slowing down the creation of new stars. On the other hand, this regulation doesn't always mean destruction. The same outflows and bursts of energy can compress nearby clouds of gas, squeezing them into regions dense enough to collapse under gravity. This compression can trigger new waves of star formation. In this sense, Sagittarius A plays a dual role, at times suppressing growth, at other times igniting it. The balance between these two effects may be critical in shaping the Milky Way's central environment. We've already seen evidence of Sagittarius A's regulating power in the form of enormous structures like the Fermi bubbles, vast lobes of gas and energetic particles extending tens of thousands of light-years above and below the galactic plane. These are thought to be remnants of powerful eruptions from Sagittarius A in the past, events that would have dramatically restructured the flow of gas across the Milky Way. Even now, astronomers detect subtle X-ray and radio echoes near the galactic core, suggesting that Sagittarius A has had multiple flare-ups over millions of years, each time releasing enough energy to alter the galaxy's gas ecosystem. Closer to home, the very orbits of stars around Sagittarius A give hints about how it influences its surroundings. Stars like S2 and others in the so-called S-star cluster zip around at breakneck speeds, their gravitational dance stirring up gas and dust in the vicinity. This constant churning could both prevent gas from settling into stable star-forming clouds and, paradoxically, help redistribute it into new regions where stars can eventually emerge. This role of regulating gas flows ties into a bigger cosmic story. Astronomers now believe that supermassive black holes and their host galaxies evolve together, almost like dance partners. A galaxy provides the black hole with fuel, and in turn, the black hole's outbursts control how much gas the galaxy can keep for future star formation. This symbiotic relationship helps explain why we see such a strong correlation between the size of a galaxy and the mass of the black hole at its core. Sagittarius A may be smaller compared to monsters like M87, but it still exerts an outsized influence on the Milky Way structure and star-making processes. There's another intriguing angle. Sagittarius A may help set the stage for the long-term future of our galaxy. Right now, it's relatively quiet, but if it were to wake up dramatically and unleash powerful outbursts, it could blow away much of the gas in the central regions, effectively shutting down star formation for millions of years. Conversely, a steady trickle of activity might keep the central region simmering, ensuring a slow but ongoing supply of new stars. In the broader picture, this regulating effect shows us that supermassive black holes aren't just passive monsters, they are architects of galaxies. By influencing gas flows, they help decide when and where stars are born, how galaxies grow, and even how long galaxies remain active. Without Sagittarius A's subtle guidance, the Milky Way might look very different. Perhaps more chaotic, with bursts of uncontrollable star formation, or more stagnant, with gas locked away and star birth stifled entirely. Sagittarius A may not shine brightly in visible light, but its fingerprints are all over the Milky Way's structure and history. Every new star, every gas cloud, and every stellar orbit near the center carries traces of its influence. In this sense, it doesn't just sit at the core of our galaxy, it helps define what the Milky Way is. When astronomers unveiled the very first image of Sagittarius A in May 2022, it wasn't just a scientific breakthrough, it was a triumph of human determination, collaboration, and ingenuity. Capturing the shadow of a black hole, something that by its very nature cannot be seen directly, might sound like an impossible task. And yet, through decades of effort and the coordination of hundreds of scientists worldwide, humanity managed to do exactly that. The project responsible was the Event Horizon Telescope, EHT, a global collaboration of radio observatories spanning the Earth. To see something as small as Sagittarius A's shadow, equivalent to spotting a donut on the surface of the Moon from Earth, astronomers needed a telescope with an effective resolution far beyond any single instrument. The solution was to link radio telescopes across continents, creating a virtual Earth-sized telescope using a technique called Very Long Baseline Interferometry, VLBI. By synchronizing these telescopes with atomic clocks and combining their data, the EHT achieved a level of detail sharp enough to resolve the black hole's event horizon. But the achievement wasn't just about hardware. The observations generated petabytes of raw data, so massive that it couldn't be sent over the internet. Instead, scientists physically shipped hard drives by plane to central processing centers, where supercomputers painstakingly stitched together the signals from all the observatories. Even then, what emerged wasn't a straightforward picture, but a fuzzy, complex interference pattern that required advanced algorithms to decode. Teams of independent researchers worked in parallel, developing methods to reconstruct the image in ways that minimized human bias. Only when multiple groups reached consistent results did the now famous ring of Sagittarius A's shadow emerge. The teamwork behind this moment was extraordinary. More than 300 scientists from over 80 institutions in 20 countries contributed, including engineers, data scientists, theoretical physicists, and astronomers. Each brought a piece of the puzzle, whether it was fine-tuning telescope hardware in the harsh environments of the Atacama Desert and Antarctica, writing code to process staggering amounts of data, or building simulations to test how different models of black hole behavior would appear to the EHT. What makes this even more impressive is that Sagittarius A posed unique challenges compared to the earlier imaging of M87 in 2019. Because Sagittarius A is much smaller, the hot gas swirling around it orbits at incredibly fast speeds, completing a circuit in minutes instead of days. This means the black hole's appearance changes rapidly, almost like trying to photograph a moving target with a long exposure. The EHT team had to account for this variability, averaging images over time while still preserving the underlying structure. That they managed to pull a clear image from such turbulence is nothing short of remarkable. The unveiling of Sagittarius A's portrait was more than a scientific event, it was a cultural one. Across the world, people saw the shadow of the black hole at the center of our galaxy for the first time, a place we cannot visit, yet which holds our galaxy together. It was a moment that reminded humanity of our shared curiosity and our ability to accomplish the extraordinary when we work together across borders and disciplines. This achievement also serves as a model for future science. The challenges we face, whether imaging even smaller black holes, mapping gravitational waves, or exploring distant exoplanets, require the same kind of global collaboration, patience, and creativity that brought us the image of Sagittarius A. It's proof that the boundaries of human knowledge expand not through isolated effort, but through collective vision. In many ways, the image of Sagittarius A is more than just a picture of a black hole, it's a mirror reflecting human potential. We look toward the most extreme environment in our galaxy, and instead of being daunted by its darkness, we found a way to illuminate it. The shadow we see at the heart of the Milky Way is both a cosmic mystery and a human triumph, showing us that even the universe's most elusive secrets can be reached when we dare to imagine and collaborate. As we bring this journey to a close, it's worth pausing to reflect on what Sagittarius A really represents, not just as an astronomical object, but as a symbol of humanity's search for meaning in the cosmos. At its core, Sagittarius A is an invisible beast, hidden by dust and distance, silently shaping the Milky Way in ways both subtle and profound. It doesn't announce itself with constant violence like some black holes in other galaxies. Instead, it waits in quiet patience, a gravitational anchor around which everything in our galaxy turns. Every star we see in the night sky, every planet, including Earth itself, owes part of its existence to this dark giant at the center. Without Sagittarius A's immense pull, the Milky Way would not hold together in its current form. The spiral arms that sweep across the heavens, the great swaths of star-forming regions, the balance of gas and dust, all are orchestrated, in part, by the gravity of this supermassive black hole. It is the silent conductor of our galactic symphony. And yet, studying Sagittarius A does more than just tell us about our galaxy's architecture. It opens windows into the most fundamental laws of physics. Near its event horizon, space and time themselves are warped beyond what our intuition can grasp. Every observation, whether it's the orbit of a star like S2, the flicker of a sudden flare, or the ghostly ring captured by the Event Horizon Telescope, is a chance to test Einstein's theories under conditions so extreme they cannot be recreated anywhere else. It's as though nature has placed a laboratory for fundamental physics right in our galactic backyard. At the same time, Sagittarius A reminds us of the mysteries that remain. How did such a massive black hole form so early in the universe's history? Why is it so quiet now, when in the past it unleashed energies powerful enough to carve bubbles stretching thousands of light years? How will it evolve in the future as the Milky Way continues its slow dance with neighboring galaxies? These questions aren't just academic, they are keys to understanding how galaxies themselves, the grand building blocks of the universe, live and die. Perhaps the most humbling aspect of Sagittarius A is that, for all its immense power, it poses no threat to us here on Earth. At 26,000 light-years away, we are safe from its grasp. And yet, despite that distance, it influences us profoundly. It defines our galactic home. It connects us to the wider story of the cosmos. And it beckons us to keep asking questions. The image of Sagittarius A's shadow, unveiled in 2022, wasn't the end of a story, it was a beginning. It showed us what is possible when humanity unites in curiosity and determination. And it reminded us that even the darkest places in the universe can be illuminated by the light of knowledge. So, as we gaze up at the night sky and wonder about our place in it, we can know that at the very heart of the Milky Way, an ancient and invisible giant is holding it all together. By studying it, we're not just learning about black holes, we're learning about the origins of galaxies, the fate of stars, the fabric of space-time, and ultimately, about ourselves. Sagittarius A is a reminder that the universe is vast, mysterious, and sometimes terrifying. But it is also beautiful, elegant, and full of answers waiting to be uncovered. And perhaps the greatest gift of all is this. In trying to understand the cosmos, we are constantly reminded of the incredible potential of human imagination and collaboration. The invisible beast at the center of our galaxy doesn't just shape the Milky Way, it shapes our quest for knowledge, binding us together in the shared journey to understand the universe itself. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. If you enjoyed the video, consider subscribing to the channel and like the video.